between it's sandwiched between between the two baths. We have the quantum system here, and then the way that we can apply magnetic field or electrical field to the quantum system, we can convey and transport heat from the hot bath to the cold bath, and then this is the way that the heat can transport, or by applying like a work to the quantum system, like applying the gate voltage, then the work can be reversed. It means that the heat can extract it from the cold bath to the hot bath and works as a refrigerator. Or another concept which is very usual in the thermodynamics is about the heat engines. It means that usually the heat goes from the hot to the cold, and then on the way, the quantum system can apply just work to the environment. These are the usual concepts in the quantum circuits in general. So, and then there are also important concepts that we try to cover here is about the ultra-sensitive detectors. So let's try to look at deeply in this system, because I will refer to it a few times in the talk. So here we have like one of these baths, either hot or cold, doesn't matter. So here, this is our bath, and then with the heat capacity of C, so it can be a normal metal, and then with the temperature T here. And then it's we have a thermal conductance, which is coupled to the phonon bath mainly, which is fixed at the temperature, like we call it as a phonon temperature or T bath. So the point is that, and then we can apply the heat to this absorber, and then the temperature can be recorded here. So the main thing is that how we measure such kind of heat currents in general. So I want to first, this system that I showed before, that we call it as a heatronics here. So I want to make a connection, let's say one-to-one connection to the electronic circuit setup, which is very usual that for use. For example, here you can see a simple RC circuit. So as you can see from the equation here, that one can write easily for the RC circuit. So we can write exactly the same for the heat setup that we are using. It means that if we are talking about the current in RC circuits, it means we are talking about the heat current here. And then the heat capacity here will be like a capacitor in the RC circuit. And then the electrical conductance with like a thermal conductance. And the main things here that we are focused on is about the temperature, which is about the voltage in the circuit. So the main thing is that here we are measuring the temperature, and by measuring the temperature, we know how our system works, and then we try to obtain everything there. Okay, so how we measure the temperature? It is a traditional in our system that we are using this NIS setup. So what is this? Is like a tunnel barrier between the normal metal superconductor, and then we have a tunnel contact in between. And then as, so based on the tunneling current here, that the formula is given here, the point is that the RT is the resistance of the tunnel barrier, and then it depends on the density of the state of the superconductor, which is not temperature dependent. And another important parameter here is the Fermi distribution of the normal metal, which is temperature dependent. And then as you can see here, so the main thing that we can, just by measuring the current, we directly see the temperature of the normal metal, not the superconductor. So the way that we are using is that here we have this LC, we have the IV of the of our measurements, and then by measuring the slope of this IV, essentially we can we have a like a universal dependence on the temperature, and then by this we can say directly we can calibrate the system based on the temperature. So this is the way that we are measuring the temperature in general. So, and then another important setup is the thermal conductance. This is the thing that we want to have. And then this is a very well-known relation from the absorber, which is coupled to the phonon bus, which and the important parameters here is the electron-phonon coupling constant, the volume of the absorber, and then it's proportional to the fifth power of the electron temperature here. This is the thing that we can independently measure in our setup. By measuring the temperature, essentially we know then the temperature, the thermal conductance to the phonon bus, and then here we have like a simple Ohm's law that we can write for the heat current. So, and then how we measure this kind of power into the circuit, this is like the simple analogy that you can see here, that if we have two resistors in the circuit, that they have a different temperatures. So, and then we can obtain the photonic power that transfer from one resistor to another. So it is a photonic power that we calculate here. So we have a resistor here that based on that, because of the temperature that it has, so it produces like a noise source, and then this noise source applies some power to the other resistor, and then we can easily obtain that, okay, so this will be the power, photonic power, which is proportional to T squared here, and then we have some coefficient here, which given by the quantum conductance in the circuit. So these are all these essential elements that we are combining together, and then we can use it here in a real circuit that you can see, for example, that we call it as a heat valve, quantum heat valve. So how it works. Here you can see schematically the circuit. So we have, as you can see, there is an element. Here we have a qubit, here like a simple squid that we can apply magnetic flux on it. And then we have two coplanar waveguide that acts as a LC circuit. And then at the end, we shunted it with our usual bath, thermal bath. So these are the reservoirs. As you can see here, this is like a copper, and then we probe it with this NIS, so we can measure the temperature. So the point is that we apply some temperature here by applying these probes. So we apply bias, and then we heat it up here, and then we apply magnetic flux here, and then we can see that how the heat goes through the other side. The usual size of this chip is about, let's say, 4 millimeter, 3 to 4 or 5 millimeters, something. So here you can see the electrical schematic of the circuit that you see here. We have this, our qubit, capacitively coupled to our LC resonator, and then we have the two thermal baths in the both sides. So the way that we are working, so I want to show it simply. So by applying magnetic flux, we change the level separation of the qubit, and then when the qubit is in the equal level size between the two other baths, so it will be in the resonance with them, and then the heat can flow from the hot to the cold one. So here we analyze them based on we consider them, each element as a harmonic oscillator. And then I want to say that there are two important parameters here. One is G, which is a coupling term between the qubit and the resonator. And then another important element here, so it's about the coupling term between the resonator and the reservoir, because there are elements that we are combining together. So the coupling here matters. And then here you can see the Q is the quality factor of our resonator here. So then which coupling is stronger, somehow it tells us that how the system works. So if we have a stronger coupling between the resonator and reservoir, it means that this is our environment, and then the squid by itself is a system. So here you can see the Hamiltonian of the system, and then the power that applies from this environment and go through the other side. So this is the energy levels of the qubit, and then here is the constant resonance of the LC circuit. And then in the 2 points, by by changing the flux here, changing the flux in the 2 points, it will be in the resonance with the qubit, and then the heat we have in these two sharp heating, and then there will be no contact between the qubit and the environment, so nothing goes through. Here you can see the experimental data, and then here the theory modeling for that the only parameter, fitting parameter here is the quality factor, as you can see. Okay, but let's go to another regime. The interesting thing is that we saw another regime which is more convenient for those guys that they are working with the qubit stuff. Here we have a stronger coupling between the qubit and then the resonator. The point is that now we will end up to be in a totally different regime. So here, this qubit and the two resonators, it will combine as our quantum system. So let's say then in this case, only reservoir will be the let's say perturbation that we apply on this quantum system. So then the Hamiltonian in this case is given by the energy of each resonator, and then the qubit, and then the coupling of the qubit to each. And the important thing is that the coupling between each, between both resonators together. And then here we have the coupling with coupling to the bath. You can see that the GQ here in this case is about 1. So here the power is a little bit more complicated than the previous ones, and then you see that how the power here look like at the different temperature bath here, and then how the model here we have, which is again is given by the only quality factor is the only fitting parameters here. So these two regimes were really interesting to us, and then somewhat it was a little bit puzzled that, okay, how is the real, somehow, of course we had a nice theory for that, but here I want to use this opportunity to advertise our new work here, which is in progress, and then I promise that soon it will be on archive for those ones that they are interested in this, so they maybe find it useful or interesting. So here we consider as a qubit, which we have like a resonator and our bath. So we consider this bath as a many of these harmonic oscillators, like a bosonic bath, 10 to 6, let's say harmonic oscillators, and then we try to see this local global. Of course, the point is that here is a known topic, but the things that we used here differently is that we want to really connect between this setup to the real, let's say, setup to the real experimental setup, and then how this works in the real setup. And then we try to see that when we see when we excite the qubit, how it conveys, how they decay into the bath via this resonator. The point is that here we wanted to see that where is the crossover between the local and between the global regime, when it happens, and then it depends on which parameter and how it happens that it is once in one regime and then it go to the other regime. Okay, but then let's go back to the simple setup that we have. Quantum system in between the two reservoirs. Point is that can we somehow, this works as differently? So meaning that how it will be that if we bias the temperature differently between the two reservoirs, is the power that goes from one side to the other side will be equal? So the point is that if there will be equal power from both sides, it means that it is a symmetry system. And then if not, it means that there is asymmetry in the system. It means it works as a cube. It works as a diode here. So it means that when the power forward, it will be different a little bit with the power reverse. So then we can call it as a quantum diode, or it works as a rectifier. So there are a few experiments that shows that the rectification in this setup. So the main thing is that it shouldn't be symmetry. It means that first of all, and not linear. So it means that the qubit should be really as a non-linear element there. And then if you want to boost the somehow the rectification ratio, it means that we can even make more asymmetry in the system. So it means that not to have an equal coplanar waveguide, the resonator. So we can make them as a different. So you can see that I'm going to see in this set, because the previous regime, as we called it as a local regime, it will not be working, because the qubit cannot be at the same time in resonance to the both sides. So that's why we are sitting in the global regime for the rectifier only. So here you can see the experimental setup where we have the qubit, and then we have two different LC resonators, 3 and 7 gigahertz. And then we can see again how the power, when we are making the different temperature between this side and this side, in the both side, we look at the power in the forward and power in the reverse. You can see that how it looks like in reality in experiment, and then even you can see that how even the shape of the power, it's different here. And then the ratio of these two, it gives us the rectification that we could somehow see about 10% rectification in this setup. Okay, we don't have any theoretical model for that. This is like an open question that how this power works here. So that's why this system looks a little bit complicated. That's why we try to make it even more simple. As you can see here, we have this can be better. We have a qubit, and then we have a different coupling to the two bath. And then we can see that we have a transition up, transition down, which is given by the main important elements here is the coupling between each reservoir and the qubit. And then another thing is about the temperature, which is given by this beta 1, beta 2, which is the inverse temperature of the bath 1 and then the bath 2. So in this case, the power, which is given by this expression, and the rectification ratio, which, as you can see, when we keep one of the cold baths at the 0 temperature, which in our case, meaning like 10 milli-K, it's already enough. And then based on the dry fridges, we can really reach this temperature. Then we can see that we have a really rectification ratio based on the two important elements, which is the coupling. That's why we try to have another second generation of the heat rectifier. This is the ongoing project. But as you can see here, we remove the coplanar waveguide here, and then we make the simple setup in order to somehow make it easier to understand how the rectification ratio will work here. And then you can see that one of our postdocs that's working on the setup in general here. So, and you can see in the real circuit how it looks like. It's about 800 or 1 millimeter wide here. So, and we can see that in general, the circuit looks like here. So it's easy to understand it. So here we can see that either we look at it as a linear element and look at it as a classical heat transport through this system, or look at the qubit as a nonlinear element and look at it as in the quantum model. So this is an ongoing project. I'll just show you some of the few experimental data and then rough estimation of the theory model for that, so which is not accurate yet, but I just wanted to say that what is also going on in this direction. Okay, another things that it is important till now, whatever I mentioned, is that how we can, the temperature, we measure the steady state temperature. It means that we stay when the whole system with the bath in the equilibrium. And then we have a mean value of the temperature. But what else if we can see the time dependent of the temperature, which we can also give us a lot of opportunity to measure many things. So here I'm going back to the real setup that we have, which looks like a simple, but it can be, it is very deep. So here we can see that while we are applying heat, let's say now pulse heat to the reservoir, So then if the temperature of the bath is equal to the our absorber here, then because of the pulse, we have a rising in the temperature, which proportional to this energy from this quanta divided by heat capacity. And then if nothing else happens, then the temperature relaxes back based on the time constant C over G thermal. So this gives us the energy resolution, which is given by this expression here, C G thermal ST. It meaning that we should have as weak as possible the thermal conductance to the phonon bath, heat capacity, small heat capacity, and ST, which is a spectral spectrum of the temperature, let's say noise equivalent temperature for the thermometer. So I want to focus on the how we can somehow boost or optimize the temperature detection that we have, let's say our thermometry that we can measure it based on the time. So here, this is the way that we have our setup. We call it ZBA, zero bias anomaly bias thermometry. And then we put this one into the lumped LC circuit. So it means that, as you can see here, this is our structure, and then we put it into this LC circuit, and then we try to measure this in the RF setup. So here, if we apply this, this is input, and then this is the output, and then the ratio between these two, output divided by input, is given by this S21, which is proportional to the conductance of the absorber. So here you can see that we have this NIS. But now we added another superconductor here. So we call it as a SNIS. So the things that this clean contact is doing is that this clean contact induced some proximity effect to this normal metal. And then as a result, if we see that this is for the conductance of the normal metal, if we apply this clean contact here, then we can see some anomaly around the zero. So, and then this anomaly, it is temperature dependence. And the good thing is that you can see that here, this conductance at different temperatures, you can see that how it becomes deeper at the lower temperature, and then it becomes shallower at the higher temperature, which is now you can see that even at the low temperature, we have a linear calibration. This is very important for us because the important thing is that for the usual NIS, we lose the sensitivity towards the lower temperature, and then we have a very good sensitivity at higher temperature. But this is not important for us because we want to have a thermometer that works as low as temperature that is possible for us, because this is the regime that is interesting for us. So, and then linear calibration is also helps a lot because it makes things more systematic and then makes it even better how to apply it. So here you can see that I showed it the data for the optimized distance, because we had it for the different distances, starting from half a micrometer to 50 nanometer. So it means that this distance to here is about 50 nanometer, which is the best now for us, because lower than this is very difficult to make, and higher than that we lose the sensitivity. Here in the RF setup, you can see that we have a good calibration, and then in the even it's possible, as you can see here, how to measure in the DC setup, and then we have a super nice linear calibration down to the very low temperatures. So it is now we have the set. So how we can use this thermometer here? So let's say go back to the analogy between the electrical circuit and then these heatronics or these heat circuits that we have. About a century ago, Johnson and Nyquist find the noise in the electrical circuit, which is given by this expression here, related to proportional directly to the electrical conductance and then the temperature here. So now, if we make again one-to-one correspondence to our heatronic structure, Again, at the low frequency regime is given by this equation. Why T squared? Because now we are talking about the energy, not talking about the current here. And then the important element here is that we should have a thermal conductance to the phonon mass. So now here again, for the difference temperature and difference heat current, we have our Ohm's law. And then the temperature fluctuations at low frequency is given by this expression here. So then the main element here is about the thermal conductance and of course the temperature. Of course, if one can use the full bandwidth of measurement, so then we have a cutoff at the omega c, which this omega c is given by this G thermal divided by C, which is the heat capacity. And then if one can integral over all frequency, we have this somehow this expression which only depends on the heat capacity, not thermal conductance. But here we stay at the, we are not measuring with the full bandwidth, only the low. So it means that the element that we can directly measure is about the thermal conductance. Okay, so now let's go to the real setup. How this temperature fluctuation works. The point is that while we are measuring, of course, the mean value of the temperature, because it's in equilibrium with the phonon mass, is constant. It doesn't change. But the point is that because our absorber is all the time coupled to the phonon mass, so it means that there will be like a exchanging energy between them. These energy are different. So this is one thing. Another thing is that they have at the different times. So these two elements are the important elements that gives us some fluctuations to the temperature, as you can see in the real data, that how we see them. And then this is somehow the things that limited us while we want to measure the real things. When something like a single event happened in a fraction of a second, and then we should be able to see. So we should be able to detect it, not it will vary into our noise signal. So that's why we want to have a as calm as possible absorber that we have. So for this quantum detector. So now this point is that if we have some coming energy also to this absorber, we can turn it to the non-equilibrium case, because when there is somehow quiet, nothing happens, this is in equilibrium, and then we can run it into the non-equilibrium case. Okay, so let's see that how it happens. It seems that the only things that limited us is the phonon mass. So you can see that this is the expression that I saw in the equilibrium noise. And then here I explain how we obtain this. And then based on that, this square root of this spectral density of the noise, that we called it noise equivalent temperature, which is important while we are talking about the detectors, is given by 1/T here. So if you see the data at each temperature, so we should expect that 1/T dependence on the temperature. But we saw one crossover that start to bend down at the lower temperature. So that's why we wanted to understand that where this anomaly comes from, where this feature comes from. So that's why it seems that the phonon mass are not the only things that limited us while detecting. So we have another terms which comes from the photons, like a tonalic environment. This is somehow something happens because of we are in this quantum regime. So all the environment can work as like a RC or like a quantum photons tunneling here. And then the point is that if this alpha times G, which is our thermal conductance here, and then the T is a temperature. So then the thermal conductance will be based on the contributions of these two terms. And then in this case, the noise equivalent temperature will be proportional at the square root of T. It means that at low temperature, the things that limited us is this quantum regime. And then at high temperature, this is the phonon mass will contribute into this case. So now I want to show you that, okay, if we pick some, because we are interested at low temperature, if we pick some experimental data into this real set, so that you can see here, the things that limited us, this is like a prohibited region. It comes from the fluctuation dissipation theorem. It means that whatever absorber it is, it's somehow limited by the phonon mass. So no one can go below this region. And then you can see that our experimental data is somehow very close to this region. It means that our absorber is as calm as possible, meaning that we have a non-invasive detector. So then how it works? It means that if we want to detect something in this regime, which is like a microwave photon, it means that we should be in this blue area. And then our detector already is calm. It means that if we have some energetic quanta to the absorber, already we can measure. So now, this is something that this is our next step. You can see that our planned experiment here, so this is almost half of the circuit that you usually see, and then this is the things that we need, that we have a qubit as a photon source, and then we have our coplanar waveguide as a filtering effect, and then we now use our new setup, which is our zero bias anomaly thermometer. So the things that we can see here is that we can see the quantum jump into this somehow quantum circuits, meaning that if we try to excite the qubits, then the qubit starts to decay, and then the decay rate is given by this red dashed line here. So it starts if nothing happens, which is not, it is unusual. It means that anyway, it will somehow jump, it will relax to the bath, and then every now and then at random time, we will see some jump. Okay, so, and when each jump happens, the things that it will happen is this event happens in hours. So this is like a response from the detector that we will be able to see. Here, there is when there is no jump here, this is based on the real parameters that we introduced, that how we can see such kind of things. So based on when there is no jump, so it means that this is the calmest possible phonon bath that we have. And then if some energy, one of those jumps happen, so we will see it in our detector, and then it will relax back to the bath temperature. So the different red lines, it depends on the different response time of the thermometer, that how this detector is fast enough or not. And then based on the parameters that we have, the real parameters, we are close to the black line. It means that in the signal to noise ratio here is 10. And of course, it will be practically possible to see such events, but we will be somehow limited by other things. That's why, so we have another option, so which based on the previous works that I advertised, we also look at another option in order to boost the signal. It means that even if we can decay this like a splitting photon, decay this to the two different baths, it means that this is the decay of the photon, and then this is the response in the two just not uncorrelated baths. This is very well known into the experimental things by using the cross correlation measurements, because with the cross correlation measurements, one can easily boost and promote the signal and increase the signal to noise ratio. So there we explain it very well, and then I hope that you will see it on archive soon. So here are the main collaborators from the present work that I presented, my supervisor, Professor Pekola, and our postdoc, Yu Sheng Chang, and then other doctors here that you can see, and then they just mainly contributed in the present work that I presented. And then here our main collaborators from different universities, and that mainly contributed in the theory part of the work. And then with this, I want to summarize my talk, which I covered here. Thank you very much and for your attention. Yeah.
Okay, thank you very much, Bayan, for this very nice and clear talk about the, I think, impressive results that you've done in the experiment. So also thanks for the timing. We are very well in time now, so we have time for questions now. So you can raise your hand if you have a question. Okay, I can start with one, so I break the ice.
Yeah.
So I guess the idea with one of the possibilities for these thermometers that you talk about in the last part, this allows you to measure the counting statistics of emitted photons, for example, in the qubit.
Yes.
Okay, but for this, would you need some kind of well, if in a qubit the frequency of the photons will be well defined, I guess. No, so
Yeah, absolutely. It depends on the design of the qubit, that the level separation of the qubit that we have. So it is easy to adjust. So mainly the typical number that we are using is about 10 to 20 gigahertz. So for example, if we have a 10 gigahertz photon, which is very usual, and then this is the numbers that we are using, it meaning that we have a half a Kelvin energetic quanta, and then for the 1 Kelvin we have like a 20 gigahertz photon. So all these experiments that we saw is about this 1 Kelvin quanta energy for 20 gigahertz energetic photon. And then based on the numbers that we have, it's possible to see them in our quantum detector, which is somehow, and then we will have 10, our signal to noise ratio is about 10 here.
Good, thank you. Any other question?
No questions in the chat.
In the chat, there is nobody. Also, the younger people can ask questions. There is one by Alessandro.
I have one concerning the rectification. Which is the stronger rectification that you measure or not? I mean, have you measured the rectification, and which is the stronger?
10%. 10%. Actually, yeah, because it's the things that we measured, it was 10%. That's why we have another design for the second second generation of the rectification that we have, and then we wanted to increase it. So, but we couldn't measure higher than 10%.
Okay, that's it.
Yeah.
Thank you.
Okay, Alfredo, you can.
Hello, thank you for the talk. And I was curious about why you say you have difficulties to fit with the theory for the rectifier in the case where you have the resonators, asymmetric resonators, coupled to the qubit.
Yes.
Why is that?
You can see that here, while we have this heat valve, so meaning that we had essentially the same set with the qubit, and then two equal, let's say, our resonator here. And then we could being in the two different regimes, and then try to give a theory model for that. But then we end up to having a little bit more difficulties to, so there were some other parameters that play the role here that we get very close somehow shape for the power, but essentially because the shape of the different side, it will be different. So we couldn't make it somehow, because it depends that while we are have this quantum system, let's say, then it depends that the noise of each resistor, how it apply on the full quantum system. And then here, from both sides, we couldn't make it like a totally different. We could have a rectification ratio, but we couldn't capture all the features into the shape of the power. That's why we try to make the circuit even easier, and then here we try to remove these coplanar waveguides. Now this is somehow in a regime that we can somehow study better and then try to estimate the power. Actually, Joachim Ankerholt from Ulm University, just he's working also in these teams, and then we find it that okay, it needs more work. So then maybe in the near future we will try to find out that how the power look like. Yeah. Okay. And then I think that he has soon, it is not an archive, but as far as I know, that there will be some paper ready for that, only theory part. that it will show and somehow predict how the power look like here in this kind of setup.
Okay. And Rafa, if you allow me, another question is...
If it's fast, yes.
Okay, fast. Excess quasi-particles, you didn't mention that they play a role in these experiments. Is this so? Or because you always have this in equilibrium, the reservoirs? So.
Actually, in this kind of new set that we have, because the way that we are measuring, we saw some anomaly in the absorber that we have, and then it seems that this quasi-particle current really play a role here. Then it means that we should take that part, that one also into account. And then, but when we have this, the qubit is now very damped, and then in this case, I'm not sure that. Okay, of course, this is the thing that we should look at it. But in this current experiment, we saw that this quasi-particle current also affects on the absorber in general. And then this is not the thing that one should neglect it, for sure. Yeah.
Okay, thank you very much.
Okay, so thank you, Bayan, for the nice talk again. And now we go to the next speaker, which is Bjorn Schotman, and he will talk about the topological Josephson junctions related to phase coherent caloritronics.
Okay, so let me start by thanking the organizers for setting up this very nice and interesting mini colloquium, and also for inviting me to give a talk here on our recent work. The results that I'm going to present today come out of different collaborations with my PhD student, Alexander Bauer, and my postdoc, Sun-Young Wang, and there will also be some work done in collaboration with Evelina Ankiewicz from the University of Würzburg. So what I'm going to talk about today is a mixture of two things that seem rather incompatible at first glance. There's phase coherent caloritronics, so heat transport, which is dissipative, and topological Josephson junctions, where people are typically interested in Majorana fermions and don't want to deal with dissipative effects at all. And what I want to do in this talk is to convince you that you can actually put these things together in a meaningful way, and to actually use phase coherent heat transport as a tool to learn something about the topological properties of Josephson junctions. So here's a brief outline of my talk. I will first start with an introduction where I introduce you to these two concepts of phase coherent caloritronics, and also wrap up the important ingredients of topological superconductivity that we need. And then I will present two example systems that we have looked at. The first one is the Josephson junction based on superconductor topological insulator hybrids. And then the second example is a Josephson junction where we have intrinsic topological superconductors as the reservoirs. And then I will conclude by giving some summary and outlook. So let's start with the phase coherent caloritronics and look at some theory. And let's take a look at the simplest superconducting element that you can think of, a standard Josephson junction consisting of two superconductors that are connected by some insulating barrier. And now if you apply a bias voltage and some phase difference between the superconducting order parameters, there will be some charge current flowing that has been calculated back in the 60s by Josephson. And what he showed is that there are basically three different contributions to the charge current. The first one here is due to the quasi-particles which are above the superconducting gap. And that's a dissipative process, so this requires a finite bias voltage to be applied between the superconductors. And this term is independent of any phase difference because the quasi-particles don't know about the condensate. The second contribution is the famous Josephson current, which is due to the coherent transfer of Cooper pairs between the superconductors. So this is a dissipationless process that flows even in the absence of a bias voltage and is driven by the superconducting phase difference phi. And finally, there's a third term, which is often not discussed, and this arises from Andrea reflections, where quasi-particles above the gap can actually talk to the condensate. So this term is also dissipative, so it requires a finite bias voltage, but since quasi-particles talk to the condensate via the Andrea reflections, there's also some phase dependence. And this is sort of an issue because if you apply a voltage, the phase becomes time dependent, and then this term is averaged out. So it does not really play a role if you look at DC transport. Now, shortly after Josephson looked at this charge transport, there were Markey and Griffin who looked at a temperature biased Josephson junction. So we have now different temperatures and possibly a phase difference. And they calculated the heat current that flows in response to this temperature bias. And what they find is that the general structure of the heat current is very similar to what Josephson found for the charge current. So there's one contribution from quasi-particles above the superconducting gap that's phase independent and requires a finite temperature bias. In principle, there's also a contribution from the Cooper pairs, but as long as you don't apply a bias voltage in addition to the temperature bias, all the Cooper pairs are at the same energy, so they don't contribute to the heat current, and this coefficient here is simply 0, and you can forget about this term. But importantly, there is this third term arising from the Andrea reflections, which is now again phase dependent because quasi-particles and Cooper pairs talk to each other. And this term basically implies that you now have a magnetic control via the phase difference over heat currents. It turns out that when Markey and Griffin made this prediction in '65, they were way ahead of their time. Nobody really was interested in their results. The paper basically didn't get cited at all because measuring heat currents is really challenging, as Baum told us in her talk. And so it was only in 2012 that there was the first experimental detection of these phase-dependent heat currents by the group of Francesco Giasotto in Pisa. And here's the experiment that they carried out. I will guide you slowly through this because it's a rather complicated setup. So we have here in green a source and a drain electrode made from a normal metal, from copper. And you see that there are additional contacts up here and up there, which act as both a heater for the source and also as a thermometer for both the source and the drain. That's basically the same technique as we have just heard about. And in the middle, in violet and in blue, we have several superconducting elements that form 3 Josephson junctions marked by the red crosses here. And the phase difference across these 2 junctions can be controlled by changing the magnetic flux through this loop. And now the idea of the experiment is as follows. You heat up the source, so heat will flow from the left into the structure, and it can then go either down into the superconductor or flow into the drain. And so if you now modulate the magnetic flux, you modulate the thermal conductance of the Josephson junctions, and this in turn should modulate the temperature of the drain in a flux periodic way. And this is indeed what was observed in the experiment, as you can see here. So the different solid curves that you see are experimental results for different bath temperatures. And there is indeed this periodic modulation with the flux. You also see the dashed curves. This is basically the theory of Markey and Griffin without any fitting parameters, and there's just a perfect agreement between theory and experiment. And so after this first experiment, this field of phase coherent caloelectronics really took off, and there have been many works in the past years. I've here just put some papers to give you an idea and a feeling of what has been done. So there are some efforts to really come up with caloelectronic devices like a thermal diode that allows heat to flow, say, from left to right, but blocks heat flow in the opposite direction. And this has also been realized in this nice experiment here. You can also go and somehow combine two of these heat interferometers into each other and come up with a thermal router. That's what you see down here. And this basically allows you to send heat from your hot source either into drain 1 or into drain 1 simply by changing the magnetic flux through this quid by half a flux quantum. Apart from these experiments that go more into sort of applications, you can also look at more fundamental aspects. There's, for example, the option of having heat diffraction, which is sort of the thermal analog of the Fraunhofer pattern in charge transport. When you have extended Josephson junctions, this has been theoretically predicted in this PRB, and in the meantime, there have also been experiments on this. And you can also look at other transport regimes. This is some work from the group of Janine Splettstößer, where they looked at diffusive transport and discussed in how far these phase coherent and phase dependent heat currents actually survive in the diffusive limit. All right, so much about the caloritronic aspects. Let's now come to topological superconductivity. And topological superconductors, just like any other topological state of matter, are characterized by having topologically protected surface states. And for these topological superconductivity or superconductors, the key feature of the surface states is that they are Majorana fermions, meaning that their creation and annihilation operators are equal to each other. And this has some important consequences. For example, you can then come up and build fault-tolerant non-local qubits out of these Majorana fermions that you can in principle use for topological quantum computers. And this is also one of the main motivations for looking at these Majorana degrees of freedom. Now, how can you realize this experimentally? Turns out that there are only very few and very exotic materials that host topological superconductivity in an intrinsic way. So it's more common to sort of come up with hybrid structures that put together these topological superconductors. And what you need in all these proposals are three ingredients. The first one, obviously, is superconductivity. And to this, you have to add both spin-orbit coupling and external magnetic fields, because these will then work together to convert your standard spin-singlet Cooper pairs into spin-triplet Cooper pairs that have non-trivial topological properties. There are different ways how to put these things together. One direction is the use of nanowire superconductor hybrids, like in this experiment from the Kauenhoven group, which was sort of the first one to show signatures of Majorana fermions. But you can also go and combine superconductors with topological insulators, like in this experiment from the Molenkamp group. Now, if you have built up such a hybrid structure, you of course want to know how do Majorana fermions show up, say, in transport features. And there are a number of different ways. The first one is that these zero energy Majorana modes give rise to a zero bias peak in the electrical conductance, which is quantized by 2e²/h. And this has been observed in several experiments now. The first one was the Kauenhoven experiment that I showed. There the peak was not yet quantized, but in the meantime, there are indeed signatures of these quantized zero bias anomalies. However, we all know that zero bias peaks can have many different origins, so it's always good to have some alternative way of probing the Majorana fermions, and such tool exists. For example, the so-called fractional Josephson effect, which is a Josephson effect where the supercurrent is 4 pi periodic rather than 2 pi periodic. And so if you do some AC Josephson measurements, what you observe is that every second Shapiro step is missing. And this was observed here in the experiment from the Molenkamp group, where you see that when you go to low driving frequencies, there's indeed only every second Shapiro step showing up here. However, these experiments are challenging because in typical Josephson junctions, there are other 2 pi periodic modes on top of the 4 pi periodic modes. There are also issues with quasi-particles, so that's really challenging and would be nice to have other tools to probe Majoranas. The third way is to show that there are non-trivial braiding properties. That's of course very challenging, and as far as I know, there haven't been any experiments on this yet, because this requires that you can really move around your Majorana fermions, which is non-trivial. And all this sort of motivated us to say, well, maybe we can actually use thermal transport, in particular these phase-dependent heat currents, as an alternative way of probing Majorana fermions. And this is indeed the case, as I want to show you now in the remaining part of my talk. So the kind of systems that we will look at in the following are Josephson junctions consisting of 2 superconductors that are connected by some non-superconducting region in the middle. And we always consider a regime where we can describe our system in terms of non-interacting electrons. So we can use scattering matrix theory to calculate transport properties. And since we deal with superconducting systems, we will make use of the Bogolyubov-Lejeune formalism, where we double our degrees of freedom to account for the particle-hole symmetry of the problem. And so we have the Hamiltonian describing the electronic degrees of freedom up here and the whole degrees of freedom down there. And they are coupled to each other by the superconducting order parameter delta. We can then solve for the eigenstates of this Hamiltonian and construct scattering states out of this by the standard procedure of wave function matching, which will give rise to certain reflection and transmission amplitudes. And from these, we can then calculate the transmission function that will in general depend on both energy and the phase difference. And once we know the transmission function, we just have to solve this standard integral to obtain the phase-dependent thermal conductance. Okay, before I come to the topological Josephson junctions now, let me first tell you a bit about a standard SNS junction and how the phase-dependent thermal conductance looks over there, because then we have something to compare with. So we consider a short superconductor normal metal junction now. And what I've calculated and plotted here is the phase-dependent thermal conductance, and the different curves correspond to different transparencies of the junction in the normal conducting state. So up here in blue, we have a completely transparent interface between the superconductors, and down here, the purple curve then corresponds to the tunneling limit. And what you see is that as we go from the transparent case to the tunneling limit, the phase dependence changes qualitatively from having a minimum at phase difference pi to having a maximum at phase difference pi. Now, how can we understand this? Well, it turns out that actually the behavior of the thermal conductance is closely linked to the energy of the Andreev bound states that live inside the superconducting gap. How does it work? Well, let's actually look at the transmission function, which is plotted here as a function of energy and phase difference for the transparent case and the tunneling limit. And if we start by looking at the transparent case, we see that the transmission is 0 inside the gap, as we expect, and there's the Andreev bound state shown by the blue curve here, and at phase difference pi, it moves to 0 energy. And at the same time, this removes spectral weight from above the superconducting gap, therefore gives rise to a strongly reduced transmission through the junction, and this directly translates into this minimum that we see over here. The situation is different when we are in the tunneling limit, where we see the transmission here on the right. In this case, the Andreev bound state always stays very close to the gap edge. And so at phase difference pi, it's just a tiny bit below the gap. And in consequence, there is a sort of quasi-resonance above the superconducting gap. That's a well-known phenomenon from quantum mechanics. And this resonance gives rise to the increased transmission and therefore connects to the maximum that we see over here. So this is what happens in a standard SNS junction that was calculated by the first time by Zhao and co-workers in 2003. Now, what's in the topological case? So here are similar curves for the phase-dependent thermal conductance for a short superconductor Ti Josephson junction. And what you see is that all of these curves collapse directly onto each other. So there's really a universal behavior of the thermal conductance in the topological case. Why is this? Well, there are two important ingredients. One that explains why we always get this minimum here is the fact that now we have, again, this gapless Andreev bound state, which arises at phase difference pi, and which is this Majorana fermion that appears in these junctions. So there's always the reduced spectral weight above the gap, and therefore the minimum of the thermal conductance. The other question is, of course, why do all the curves collapse onto each other? And this is simply a consequence of spin momentum locking, which basically forbids any kind of backscattering in these topological Josephson junctions because there's a superconducting Klein tunneling happening. Now, when we got this result, we also wondered whether this is actually something you can observe in experiments. So we basically considered parameters similar to the experiments by Francesco Giasotto and calculated how large would a typical temperature variation in some drain electrode be. And we found that it's not too sensitive to any detailed choice of the parameter, but it's always in the range of, say, 10 to 20 millikelvin, which is also what Francesco saw in this SIS tunnel junction. So we're very confident that you can actually observe these experiments in these effects in experiment. What we then also looked at was the case of long Josephson junctions, where long means that the length of the junctions becomes comparable to the superconducting coherence length. And in this case, it turns out that you have to take into account that the wave vectors of both electrons and hole-like quasiparticles become energy dependent. And this then gives rise to this additional length and energy dependence in the transmission function. And now if you calculate the thermal conductance as a function of phi and the junction length, you see that as you increase the junction length, the maxima and the minima of the thermal conductance no longer occur at phase difference 0 and pi, but they rather move to some finite phase difference. So in that sense, it looks a bit like a phi junction behavior, but I want to stress that the origin of this behavior is different than this phi 0 junctions that you have in electrical Josephson currents, because there this is typically connected to some spin physics, and here it's really just due to the energy dependence of wave vectors. We then also looked for comparison at long SNS junctions. There, of course, you also get some effects from the energy dependence of the wave vectors, but on top of this, you also get Fabry-Perot oscillations, because now the electrons can go back and forth many, many times inside the junction and pick up some additional phase. And the combination of these two things then gives rise to a rather complicated interference pattern that is also very sensitive to the detailed parameters that you choose. And so the key message here is rather that for long Josephson junctions, you should not really expect to see any reasonable phase dependence in the thermal conductance, while in the topological case, due to the superconducting Klein tunneling, you also get some meaningful phase-dependent thermal conductance in the long junction limit. Okay, so much about the superconductor topological insulator hybrids. Let's now switch gears a bit and consider a Josephson junction where the two superconducting leads are intrinsically non-trivial superconductors. For example, two spin triplet P-wave superconductors. And the motivation for this is sort of twofold. There are some exotic materials, like, for example, this strontium euthanate, which are believed to host exotic spin triplet superconductivity. And the other motivation comes from the fact that superfluid helium-3 is known to be a spin triplet P-wave superfluid. And in principle, you could then build up such a Josephson junction with the superfluid helium-3 and measure thermal transport properties. Now, if you have a spin triplet superconductor, it turns out that this is way more complex than the standard spin singlet S-wave superconductor that we all know from kindergarten. Because a spin triplet is always something more complicated than a spin singlet. And it turns out that the superconducting order parameter in the triplet case can be parametrized in this form over here by the so-called D vector that sort of encodes information about the precise nature of the triplet pairing. And there are at least 3 different types of pairing that you can come up with. The first one is so-called helical pairing, where the D vector is just proportional to momentum. That's in some sense the simplest phase that you can imagine because it's isotropic both in spin space and also has an isotropic gap, and it does not break time reversal symmetry. The second type of pairing that we want to consider is unitary chiral pairing, where the D vector is proportional to kx plus iky. This phase is more complicated. It breaks time reversal symmetry. It also has a preferred axis in spin space, and there are also 2 nodes appearing in the gap function. And finally, the third type of pairing that we want to consider is non-unitary chiral pairing that can be realized by a D vector of this form over here. And this is sort of the most exotic thing you can come up with because in the non-unitary chiral case, you actually have a situation where just one of the 2 spin species is coupled while the other is uncoupled or unpaired. And in the following, I want to discuss thermal transport for such Josephson junctions that realize these different types of pairing, and we will see in how far you can actually use thermal transport to distinguish between the different types. So let's start with a simple helical pairing. Here on the left, you see again the thermal conductance as a function of the superconducting phase difference, and the 3 solid curves here correspond to the P-wave case with different transmissions of the junction in the normal case. And for comparison, we also have here the dashed curves, which are the standard S-wave case that we have seen earlier on. And what we find is that the thermal conductance in the P-wave case always has a minimum at phase difference pi. And this can in fact be again linked to this Majorana Andreev bound state that occurs at phase difference pi and is locked to 0 energy. So there's the reduced transmission above the superconducting gap that gives rise to the minimum in the thermal conductance. There is, however, one important distinction to the TI case that we have just discussed, because you see that now the different curves do not collapse onto each other, but rather when you decrease the junction transparency, the thermal conductance goes down. And this is because here we have a system with a quadratic dispersion, so there is no spin momentum locking, and there are backscattering events taking place at the junction when there is not a perfect interface. All right, now let's go to the unitary chiral pairing. And as I already said, in this case, there is a preferred axis in spin space for this type of pairing. And so the relative orientation of the two d vectors in the left and the right superconductor starts playing an important role. So the different curves that you see up here for the phase-dependent thermal conductance now correspond to different angles between the d vectors in the two superconductors. And when the d vectors are parallelly aligned, then we get the red curve that shows the typical behavior that we expect by now with this robust minimum at phase difference pi. But as we start increasing the angle between the two d vectors, we see that the curves become more complicated. And when we finally reach a situation where the two d vectors are orthogonal to each other, then we have this yellow curve. We find that the thermal conductance becomes a pi periodic function of phase rather than a 2 pi periodic function. And why is this the case? Well, we now have to look at the spin structure of the Cooper pairs. If we have this orthogonal d vectors, it means that in one of the superconductors, we have a pairing of spin of the type up-up and down-down electrons. In the other superconductor, we then have a pairing where up-down and down-up are coupled to each other. And we see that there's no way of transferring a single Cooper pair and conserving spin at the same time. This is only possible if we coherently transfer two Cooper pairs from one side to the other. So we transfer a charge of 4e, and therefore we expect our transport properties to be pi periodic. And that's indeed what you see here. We can also understand why there are minima and maxima occurring at these different values by looking again at the transmission function and the Andreev bound states in the junction. And you basically see that whenever there's an Andreev bound state coming close to the gap edge, then we get a maximum in the thermal conductance. And when the Andreev bound states are further away, there is this minimum in the thermal conductance. All right, now let's come to the non-unitary chiral pairing. There it again plays a role how the d vectors are oriented relative to each other. The parallel case is sort of the trivial one where we get a minimum of the thermal conductance at phase difference pi because this paired channel shows the same properties as in the helical and in the unitary chiral phase. However, if you have a situation where the two d vectors are antiparallel to each other, that's the yellow curve over here, then we find that the thermal conductance is completely phase independent. And this is because now we are in a situation where the spin up channel is paired in the left superconductor while the spin down channel is paired in the right superconductor. And so there's no coherent transfer of Cooper pairs possible at all. And therefore there's no phase dependence. And then if we are at some intermediate angle, we again have the transfer of larger numbers of Cooper pairs that give rise to higher harmonics in this phase-dependent thermal conductance. Another interesting feature that occurs for these non-collinear geometries is that there are no proper Andreev bound states anymore because there's always the possibility to leak out to either the left or to the right side for these bound states. And therefore, the transmission function is no longer zero inside the gap, but there's some finite value. And there are also no sharp Andreev bound states, but you rather get these broad resonances that show up as reduced transmissions over here. Okay, this brings me to the end of my talk. I've discussed with you that Andreev bound states in Joseon junction can affect the transmission of quasiparticles above the superconducting gap. We have also seen that whenever there are Majorana bound states present in the junction, they give rise to a very robust minimum of the thermal conductance. And in this last example, I've discussed with you how you can actually use the thermal conductance as a probe of these different types of spin triplet Cooper pairs that can exist. And if you're interested in more details, there are these three papers. The one with Evelina is on the superconductor TI junctions. The one with Alexander Bauer is on the spin triplet pairing. And with Sun Yong, we wrote this topical review on both standard and topological Josephson junctions and heat transport. And with this, I'd like to finish and thank you for your attention.
Okay, thank you very much, Bjorn, for the very nice and clear talk also for sticking to time. So now it's time for questions. I see there is.
I have one question. So you talked about this thermal conductance. So first of all, thanks for the nice presentation. So you look at the thermal conductance, but you look only at electronic thermal conductance. Are there any interesting effects if you look at phonons, for instance?
You're absolutely right. We're just looking at the electronic part. And the motivation is, of course, that these superconductors, they all live at very low temperatures only, where typically you can safely forget it about phononic heat transport. And I would also think that the phonons would not really interact with the superconductor. So, I mean, they would just be some parasitic channel that is sort of boring in that sense.
Okay, but I mean, the thermal conductance quantum which you have for the electrons is the same as for the phonons, right? So your
yes.
Phononic conductance quantum is kind of the same size.
Yes, that's absolutely right. But I mean, the point is that at low temperatures, there are no phonons. So even if they have the same thermal conductance quantum, if they are not around, they cannot contribute to thermal transport.
Okay, thanks.
I also have a question.
Yes.
So thank you for the talk. Very, very clear and very nice. So can you come back to your results with the universal thermal conductance?
Yes.
I'm not sure if I understand this universal plot for different transmission functions, because when you change transmission in a topological junction, the Andreev level dispersion also depends with a square root of the transmission. And you would, as soon as you deviate from unitary transmission, you would see detachment of the Andreev levels near 0 and 2 pi phases, and they will go down in energy. So can you explain what is actually, how do you find tau in your model?
Yes,
it's not
so
the usual tau, right?
The tau that we have here is the usual one that you have that is related to the delta barrier that you put between the two superconductors. And it turns out that for the superconductor TI junctions, the tau completely drops out, and also the Andreev bound states actually do not detach due to this superconducting Klein tunneling. I mean, that's basically this paper by Evelina Hankiewicz and Kachov, where they showed that this is the case. However, if you go to the
yeah, the rest I understand. Yeah, it's only this.
So here you only have this detachment, because here you have the quadratic dispersion.
Yeah. So I guess somehow you change tau, but you don't break time reversal symmetry, right?
Yes, time reversal symmetry is not broken at all.
Okay, so it's not the same tau as like in the Fuan-Kane paper, I guess, where you have the square root of tau in the Andreev levels.
No. So here we just have put a delta barrier with a strength Z between the two superconductors, and then this parameter Z is related to tau as 1 over 1 plus Z squared.
So kind of related question. If you, I guess in your Bogolyubov model, you only include these low energy modes. So if you include other modes in the junction, which would be there, I guess you would have strong deviations from this universality, right?
Yes, you're absolutely right. So this universality only holds if you are in this short junction limit where you just have one pair of Andreev bound states. And if you go, for example, to long junctions where you have more Andreev bound states, then you get these patterns here, which are more complicated and not that universal anymore.
Okay, thank you.
You're welcome.
Okay, I see no more questions. No, so we are also on time, so let's thank you, Bjorn, for the talk. There is no applause, so
I had one, but
can do.
Well, there is we can put
I had one, but okay.
an icon here.
Well, everybody will agree that the talk was nice. So Okay, so let's go to the next speaker, who is Nikita Kirsanov.
Hello, everyone. So,
He will talk about the Cooper pair splitters. Or he will tell about it.
can you see my screen?
Yes.
Okay. Good morning, everyone. My name is Nikita Kirsanov. I'm a PhD student at Aalto University, and I work under the supervision of Professor Gardelis Savik and Professor Pertti Hakkanen. First of all, I'd like to thank the organizers for such a wonderful opportunity to present my talk today. So I'm going to talk about our recent experimental study dedicated to the non-local thermoelectric effect in a graphene Cooper pair splitter. And this is the study which was done in collaboration with many people from many different organizations, but the experiment itself was carried out at Aalto University. So a brief plan of my today's talk. First, I'm going to talk about the theory of experiment. Secondly, I'm going to show our experimental setup. And finally, we're going to discuss the experimental results and the results of theoretical modeling. So it has been recently shown that in the NSN structures, N stands for normal metals, S for superconductor, there is non-local thermoelectric effect appearing due to the effects of Cooper pair splitting and elastic tunneling. Cooper pair splitting is when a Cooper pair inside the superconductor splits into two electrons, and those two electrons are injected into the opposite normal aisles. And this is interesting because this type of thermoelectricity, firstly, it has a very interesting mechanism which was not studied before. And secondly, it can be used as a tool for generating entangled electrons from the temperature difference. So let's just assume that we have this kind of NSN device where we have also quantum dots on the NS borders. And we will assume that we will only consider the subgap region where the energy of the incident particles is smaller than the superconducting gap. In the coherent region, it can be shown that the probabilities of elastic tunneling, this one, and the probability of Cooper pair splitting can be expressed as these simple factors. Here, tau L and tau R are the transmission probabilities through the left and the right dot respectively. And if we use just a very simple resonance tunneling model, then those probabilities is just the sums of Lorentzians. And the positions of those Lorentzians can be variated depending on the gate voltage on the dot. So this was shown in many of the papers before, so it's quite known result. Then what we have with the thermoelectricity, we first have a local thermoelectricity, which appears due to the temperature difference between the normal aisle and the superconducting aisle. And this is not very interesting. But we also have the non-local thermoelectricity, which appears to the temperature difference between this and that normal aisles. And the mechanism for it is Cooper pair splitting and elastic tunneling. So this non-local currents on the left and on the right can be expressed by these relations, where the first contribution is stands for elastic tunneling, and the second one for Cooper pair splitting, which can be written in a simple Landauer's form. So now we turn to our device. So we have a graphene-based Cooper pair splitter. In the center, you can see the aluminum superconductor, which overlaps two graphene-based quantum dots, which can be seen on this little picture. And then the quantum dots, like the gate voltage on the quantum dot, is tuned by on these electrodes, the left and the right one, and we can change the gate voltages independently. Now here on the left and on the right, we have the Josephson junctions, which play the role of thermometers, as we can measure the current through this well, these two leads are the aluminum leads, and they're connected to the via the graphene interjunction. And so basically we can measure the current through the Josephson junction, and knowing that it depends on the temperature exponentially, we can then figure out what the temperature of this part is. And finally, we have a heater, which is 2 electrodes connected to the graphene nanoribbon, and they are electrically isolated from the rest of the scheme. So this red region is where the heating appears, and the heat is then transmitted through the substrate to the main part of the device. So the heater is operated at low frequency 2.1 Hertz. This means that the thermoelectric currents have the frequency, the double frequency of 4.2 Hertz, and we can use the standard lock-in techniques to measure both currents and the conductance of the scheme. So yeah, so we can measure directly the total thermoelectric current, which is the sum of the local contribution and the non-local contribution. But we're interested only in the non-local contribution. How do we eliminate the local contribution? So assume that we have measured the left total thermoelectric current, and we want to infer the non-local part of this current on the left. So to do this, we notice that the local current only depends on the corresponding gate voltage. So if we look at the previous slide, we are looking at the current appearing due to the temperature difference between this region and the superconductor. And therefore, it only depends on the gate voltage on this dot. Whereas the non-local part depends on both gate voltages. So now if we just subtract from this measured total current, its value averaged by the gate voltage of the opposite dot, we will essentially obtain the non-local current. So here are some of the results of our experiment and the theoretical modeling. Here in the left upper corner, you can see the local currents as functions of the left and the right gate voltages. You can see that, for example, the right total current is almost independent of the left gate voltage. And this is because the non-local contribution is very small. It's only about 5%. So here you see the conductance peaks of the right dot. Here are the conductance peaks of the left dot. And here are the non-local currents, which correspond to this particular conductance peaks. So for example, this picture corresponds to the selected region of this conductance peaks and this conductance peaks. Now if we want to model the behavior of the non-local current, we would first fit the conductance peaks using our resonance tunneling model, and then we would use the fitting parameters. We would put these fitting parameters into the formulas for the non-local currents, and we would obtain these pictures, which look pretty alike to the experimental ones. So sometimes some of the conductance peaks are split, and we assume that this happens because of the phonoresonance effect. And we sometimes more like fit in the fitting, we sometimes make those phonoresonances stronger than in the experiment, because this would essentially help us to reproduce the behavior of the non-local thermoelectricity better. So we can see that the non-local thermoelectricity exhibits mode-like behavior, where the sign change appears on the maximum of the conductance peak on the left, and the non-local current is also symmetrical with respect to the conductance peaks on the right. So here you can see the main result of our study. Here is on the left, first we have, like on the left we have the experimental pictures, on the right is the results of our theoretical modeling. The first picture is the non-local current on the left of the, in the left part of the device. Here is the non-local current in the right part of the device. And these are the contributions of the Cooper pair splitting and the contribution of elastic attenuating. So we can see that the magnitude of the experimental current and the theoretical modeled currents are pretty much the same, and the behavior compares well. So we think that this is convincing evidence that we have indeed observed the non-local phenomena in our Cooper pair splitter. So I come to the end of my presentation. So basically, what we have shown, we have experimentally demonstrated the existence of the non-local Seebeck effect in a graphene-based CPS device, and we also validated our observations theoretically. The preprint of our paper you can find on arXiv. Thank you so much. If you have any questions, I'll be glad to answer.
Okay, thank you, Nikita, for the talk. You were very fast, so we have plenty of time for questions now. I see a raised hand by Alessandro Braggio, so please.
Yes, thank you very much for interesting talk. I have two questions. The first is concerning to the have you considered the possibility to look the dual process instead of looking the thermoelectricity to look the Peltier, the non-local Peltier? Because in a certain sense, it will be easier because you don't need to put the gradient of temperature that is typically difficult in these nanostructure systems. Or do you have any comment on that?
Could you please repeat? I didn't quite.
Yeah, to investigate instead the non-local thermoelectricity, to investigate the non-local Peltier effect that is the dual process. So you put a current and see that you transfer heat between the two structures, including the fact that you have a superconductor that is an under mirror. So in a certain sense, if you see a transfer of heat between right and left, you should conclude that it's the non-local process that bring you the phenomenology.
I don't think that we've considered this possibility. We all, like, if I understand the question correctly, so we only consider that there is a transmission only due to the Cooper pair splitting effect and due to the elastic attenuating effect. So elastic attenuating is when we have an electron on the left, which is then can be recombined with one of the electrons in the existing Cooper pair in a superconductor, and then the replaced electron goes to the right bead. And we have the Cooper pair splitting when an electron from the left is transmitted through the structure as a hole to the right. So these are two mechanisms that we consider to be the to be two mechanisms of non-local thermoelectricity. So we do not consider any other type of transmission, electrical transmission from left to right.
Okay. If it's a time, there is another question.
Yeah, there is time.
Yeah, I want to know how you recognize the fact that the peaks, the extra peak that you have nearby to the resonance is a Fano resonance. Because in principle, with the Coulomb interaction, you may have this type of structure.
We don't consider Coulomb interactions at all.
No, that's clear. But just wondering how you recognize that those features are Fano resonances and not eventually other things.
This is one of our explanations. We thought about many different possibilities for these peaks, additional peaks to appear, and we just assume that this, we do not consider Coulomb interactions or any other type of phenomena. We only consider the Fano resonance effect. So this is just our modeling.
Okay, thank you.
Okay, Alfredo, you have a question?
Yes, well, I think it's related because the extraction of the non-local signal is a difficult issue, no? and you gave before this slide a definition which was the average of the decay voltage, and then you give this other one in which you take it as a differential conductance. So what is the one you're using? Because the one in the previous slide is not rigorous, no, in a way.
So we know for a fact that, I mean, from the theoretical point, we know that if we average this thing over the gate voltages on the right, we will, if we take a current on the left, for example, and we average it over the gate voltages on the right, then we will get the local contribution. This can be seen from the theoretical plots. This is because when you average it, you essentially eliminate the non-local contribution. And we use this.
Why? It requires some symmetry, no, of the non-local part.
Yeah, this is probably because of the symmetry, and at least this is like our theoretical considerations show that. And we use this formula because of like we have this idea from theory. We use it to infer the non-local contributions in the experiment, and then this formula is just I just show you that, like, if we look at the conductance peaks and the thermoelectricity in the vicinity of this conductance peak, we see that yes, indeed, we have this kind of dependence. So we do not use this formula for our modeling. It's just like we see from this plots that it's true.
Okay, it's more phenomenological. Okay, thank you.
Okay. Is there any other question? Okay, if not, I have one related to the first question by Alessandro. I think you mentioned in the experimental setup that you include some thermometers in the device. Is this the case?
Yes. So thermometers are two Josephson junctions, a superconductor, graphene superconductor. So we look at the supercurrent, and the supercurrent depends exponentially on the temperature. So
yeah. So with this, you can measure the heat current, no? As Alessandro said, if you instead of heating, you drive a current, you can measure how the other one of the reservoirs is cooled down, for example.
Well, I'm not an experiment. I do not do experiment. I'm a pure physicist, but in this particular experiment, we used it as thermometers. We didn't use it for measuring the thermal currents or any other stuff. We just use it for the pure reason that we need to have some kind of a thermometer to measure the temperature here and here.
Overall temperature. Okay. Okay. Thank you very much. So, if there are no further questions, I thank you again, and then I welcome the next speaker, which is Pablo Busset, and he will talk about how to detect Andrea states with unconventional pairings with thermoelectric effects. So please, Pablo.
Okay, do you see the screen?
Yes.
Full screen and mouse?
Everything.
Okay, thank you. So, hola, everybody, and thank you for the introduction, Rafa. And I would like also to thank the organizers for this opportunity to talk some physics during confinement. And this work I'm presenting was mainly done by Tony Savander, who is a master student at the group of Christian Flint at Aalto University, in collaboration with Tamura Sun, a postdoc of Tanaka Yukio groups at Nagoya University. And the main, let's say, take-home message here is expressed in these plots. So we studied the thermoelectric effect in ferromagnet superconductor junctions, a thermoelectric effect that is entirely due to Andreev processes that combine electrons on holes to form Cooper pairs in the superconductor. And as such, this Andreev thermoelectric current that I plot here as a function of the temperature bias is very sensitive to the presence of Andreev bound states at the superconductor. The positive current is what happens when we have an Andreev bound state, and there is a sign change when there is no Andreev bound state. And I will explain the details of this in the rest of the talk. And this is the preprint that we have in arXiv. So first, a little bit about Andreev scattering. Cooper pairs in a superconductor can leak to a non-superconducting material when they're put in electric contact in a process called proximity effect that I represent in this beautiful picture of a merging of rivers at Geneva. The superconductor here, at least the way I see it, will be the Rhone River on the left, and the leakage of the Cooper pairs are represented by this light blue colored water that permeates the other non-superconducting material. The effect of this penetration of Cooper pairs is that superconducting correlations are induced on the non-superconducting material, allowing for a type of process that is called Andreev scattering, where an electron on the non-superconducting material can couple with another electron to form a Cooper pair on the superconductor, leaving an empty state or a hole behind in a process called Andreev scattering or Andreev reflection. In some cases, unconventional superconductors have an anisotropic pair potential that gives rise to localized states at the surfaces of the superconductor that are take place below the gap energy. It's shown a little bit here in this high cuprate spectral dispersion. At the bulk of the superconductor, you have a gap, and at the edge, you have this resonance. And if you do some tunneling spectroscopy of this material, you will see the typical gap profile of the conductance or density of states in the bulk, and a zero bias peak that represents the presence of this Andreev bound state at the surface of the superconductor. When these bound states occur naturally in some materials, they give us information about the pairing mechanism that is taking place. But very recently, they have become trendy because we can actually engineer them or artificially create them in junctions involving conventional superconductors without any bound state. We're in proximity to some materials, usually with a spin orbit coupling. And this is a famous example in the group of Covenhoven, where they see that there is a zero bias peak emerges after some critical value of an applied magnetic field. And that meaning that some kind of bound state, they say Majorana type bound state, appears at the edges of this nano ribbon. So on the other hand, let's say the importance of these artificially engineered bound states are that are being proposed to do some very robust quantum computations. On the other hand, as everybody in this colloquium will agree, there is an interest on thermoelectric effects in modern devices. And the idea is that we can use the heat that is generated in these devices and transform it into useful electric work to increase the performance of many of these devices. The concept will be that if we have two reservoirs at different temperatures connected by some quantum channels with some transmission, the current between them follows this expression that is the integral of the transmission and the difference in the Fermi distributions. And when there is no applied bias, when there is only like a temperature gradient, the difference in Fermi distributions is completely antisymmetric, meaning that there will only be a thermoelectric current or electric current from this temperature bias if there is an antisymmetry in the transmission, which means there is some kind of broken particle hole symmetry taking place at this system. So in a very hand-waving argumentation, you could say that at low temperature, these effects will be very small because they depend on the Fermi energy of the inverse, which is small. But if you include superconductors, the relevant energy scale will be the superconducting gap delta, and you could have very large effects. And that was indeed proposed theoretically and then measure experimentally very recently. The idea here, at least in the experiments, was to take some very thin superconducting film and put it in contact with a magnetic material, so we can induce the exchange field of the magnetic material on the superconductor without breaking superconductivity, but enough that we can spin split the density of states. And then when we apply some temperature gradient by some heating current between some of these electrodes, we can inject particles, quasi-particles with majority spin over the gap that are not completely compensated by the minority spin quasi-particles that are removed from the superconductor, because there is an asymmetry in this polarization. That indeed gives rise to some thermoelectric current, as was measured in these experiments by Collenda and collaborators. So what we're trying to propose here is to say, can we do these large thermoelectric effects with unconventional superconductors? And there are obvious challenges. Experimentally, having these thin films maybe is not so easy. Putting them in contact with magnetic materials, some of these unconventional superconductors could be very sensitive. And also, and most importantly, the transport, if it's dominated by quasi-particles that are above the gap, they will be insensitive mostly to the presence of Andreev bound states. So what we propose is an Andreev thermoelectric effect that will take place when we can induce superconductivity on a ferromagnetic region by leaking of Cooper pairs that then will have some kind of interplay with the exchange field here. And as I kind of suggested before, this Andreev thermoelectric current will be very sensitive to the presence of bound states. It will change sign in their presence, and it will be formed by a mixture of singlet and triplet Cooper pairs. I will try to explain and convince you of this in the rest of the talk. So first, about the setup, we consider ballistic ferromagnet superconductor junctions. We describe them with the Beaulieu-de-Gennes equations that include the electron and the whole degree of freedom and some pairing per potential that also has a structure in spin space. We only consider pairings that couple opposite spins, but we let them have some orbital dependence, and they can be in either singlet or triplet states to more or less represent many known and conventional superconductors. And the electronic degrees of freedom we describe with this single particle Hamiltonian. And the control parameters here are the strength of the barrier that we put in between the ferromagnetic region and the superconducting region. With the exchange field, this parameter will be very important later, X, that we induce on the ferromagnet. And at some point at the end of the talk, I will consider the possibility to also have a magnetic barrier in this intermediate region that will also have this strength set M. So the scattering, we don't consider electronic interactions. We describe everything with a scattering theory. And the scattering processes that are allowed, if we inject, let's say, a spin up electron, it can be reflected, normally reflected, preserving spin, or Andreev reflected, changing the spin from up to down. And it can also be transmitted as a quasi-particle on the superconductor. So we consider translational invariance at this interface, which determines that all the transport modes depend on this azimuthal angle because the component of the wave vector parallel to this interface is conserved. And we see that the bandwidth in the superconductor, we consider it a large bandwidth approximation, and it's this Fermi wave vector. But on the ferromagnet, we can have a different bandwidth depending on the exchange field. Indeed, if we consider that the spin up is the majority spin, this is an energy sketch of an Andreev reflection from a spin up electron into a spin down hole. And even if we are within the band and with a finite density of states, for a given energy, we can find a case that with the angle of incidence, we will see some effect that gives a spin particle hole breaking term. Indeed, if we inject particles below a critical angle here, for majority spin up, they can be Andreev reflected with a spin down. But if we are over this angle, the particles can still be transmitted into the superconductor because their component is smaller than KF, but they cannot be Andreev reflected. We call this process virtual Andreev reflection, and it will not contribute to the current. And then if the angle is larger than the second critical angle, they cannot be transmitted and they can only be normally reflected. So therefore, they also do not contribute to the current. So this is the conductance. We see that there's only two types of processes. Below the gap, we have Andreev reflections for some particular angles of incidence. And the rest are just quasi-particle transfers, mostly taking place above the gap. And there is a second contribution to this asymmetry or a spin split particle Hall symmetry breaking. That is the polarization. When we combine the contributions from both the spin channels, the minority spin one has a lower weight that is determined by this formula. So when we put everything into the current, and we see that there is no applied bias, only a temperature gradient, which is represented by this difference in Fermi distributions, we see that we will only have a thermoelectric current if there is an antisymmetric part of this conductance, which will come from these two particle Hall symmetry breaking mechanisms that I described. So let's start now with an example. We consider this D plus IS pairing, which was proposed as to explain a splitting of a zero bias peak in some high TC cuprate superconductors. But for us, the only thing that matters is that it's kind of a toy model that allows us to include some very easy temperature dependence. But the important thing is this parameter delta 1 that allows us to go from a fully gap S-wave conventional superconductor when this delta 1 is 0 into a unconventional superconductor with a zero bias peak, that is the XY wave case. This is the energy momentum dispersion, and this will be how the pairing looks like in momentum space. And when this node is aligned with the direction of transport, there is a zero bias Andreev bound state, zero energy Andreev bound state, that we can split by including a little bit of this S-wave component. So indeed, we see in the tunneling conductance that there is a splitting when this S-wave component is finite, that it separates the Andreev bound states equally from the center. So we can tune our model from the zero bias peak into something more gapped. And here we have applied some exchange field, but it's hard to see the antisymmetry, but it is there. We can take the antisymmetric part of this conductance. And we see that there is some kind of Fano-like resonance at the position of each one of these Andreev bound states. And when these bound states are well separated in energy, the big contribution to the current, which is the product of this antisymmetric part and the difference in Fermi distributions, represented here as this gray dotted line, is coming from the values of energy, let's say from 0 up to the resonant value. And they have the opposite behavior as the difference in Fermi distribution. So the result is some negative current, as seen here. On the other hand, when these resonances merge around 0, they just have one kind of Fano-like resonance that has the same behavior as the difference in Fermi distributions. And this gives rise to a positive current. The important thing here is that all this antisymmetry takes place inside the gap. So it's only due to Andreev processes. And indeed, the total current without applied voltage is just given by the Andreev component of the current. That's why we call it an Andreev thermoelectric current. Can we have quasi-particle contributions? Yes, but we need to have some kind of asymmetry with we need to break the rotational symmetry of this pair potential. So in some cases where the pairing is very anisotropic, like this one that I'm showing here, it's important to know what is the relative orientation between this pairing and the interface. And we control that by alpha. If alpha is not exactly oriented in some highly symmetric directions, we will have a breaking of this rotational symmetry and a contribution of quasi-particles that we see here in this inset. And in most of the cases we have analyzed, it is finite, but it's smaller than the Andreev one. And especially if we are close to one of these highly symmetric orientations. So enough with the example. Now we check many possible cases. I'm probably running a bit of time. So let me go a bit quickly here. We have some pairings that feature some Andreev bound states, like px wave and dxy wave, and they have a very positive thermoelectric current. We have examples like this dx squared y squared, which is the same one as this one rotated, or the conventional S wave that show a negative current. There is also like one, sometimes 2 orders of magnitude difference in the current. And there is some special case, this chiral one, that requires a little bit of comment, because this chiral P wave has this chiral Majorana state inside, and it has a positive current. The chiral D wave, on the other hand, has 2 of these states, but it has a negative current. And the way we interpret this is that they are away from 0, these 2 states, and around 0 momentum that is normal incidence. So that is the biggest contribution to the current. But also, if we analyze each one of these modes separately, we see that these 2 resonances are always separated, like in this case before. So they would always give a negative current. And indeed, we have a very large negative current here. So we have also considered the possibility of having this ferromagnetic insulator. And to be very brief here, the effect of this barrier is to enhance the current when it's favoring the spin majority, or to reverse the sign of the current when it's favoring the minority spin. But even when you reverse the current, you reverse it for both cases. So there's still a sign change between the pairings with Andreev bound states and without. And finally, if I still have 1 minute, we can do some analytical algebra on this formula just to connect our results to the symmetry of the Cooper pairs. Indeed, the whole effect comes from having a different type of Andreev reflection for spin up electrons and spin down electrons. So we can define a singlet and triplet scattering amplitudes as the antisymmetric or symmetric combination of these amplitudes. Obviously, if there is no exchange field, if this is a normal metal, only one of these amplitudes is finite, the one that comes from the superconductor. But when x is different than 0, we have both. And putting these formulas into the expression of the conductance, we have, with some algebra, to express 2 terms. One of them cancels out after angle average. There are more details in the paper. And at the end, we have that the whole current is just proportional to this exchange field and the product of a singlet and triplet scattering amplitude, meaning that the current is only possible if there are singlet and triplet Cooper pairs coexisting at the junction. So with this, I will give the summary. I repeat the story that we have an Andreev thermoelectric effect, very sensitive to the presence of Andreev bound states, and there are more details in our paper. So thank you very much for your attention.
Okay, thank you, Pablo, for the talk. We have time for a couple of short questions. If you can raise your hand. No, okay, I will then do it. So in the talk by Bjorn, in the beginning, he saw that he was discussing this experiment on the thermal conductance of a Josephson junction, where the thermoelectric current was due to interference of quasi-particle and Cooper pairs. No? Do you expect, so what would be the case here? Do you expect some particular behavior of the thermal current, not the thermoelectric?
So if we look at thermal current, we're looking at, instead of the antisymmetric part of this conductance, to the symmetric part of the conductance. Mm-hmm. So there's definitely some thermal current flowing here. But I would say then that probably it's not so clear to connect it to these Andreev processes, because we're not exploiting the difference between this Andreev for a spin up and Andreev scattering for a spin down. Yeah, but kind of, it would probably have a bigger contribution from quasi-particles, but we have not checked that in detail. Yeah, that could be the next follow-up.
Well. Okay, so if there are no more questions, thank you, Pablo, again for the nice talk.
Thank you.
And next one is Gian-Michele Blasi.
Yeah.
From PISA, he will talk about he will continue on thermoelectrics in superconductor topological insulator superconductor junctions.
So yes, can you see the screen? And
yes.
Can you hear me? Okay. So good morning, everybody. My name is Gian Michele Brasi. I'm from Scuola Normale Superiore of Pisa, Italy. Today, I'm going to talk about this work I did together with Fabio Taddei, Matteo Carrega, and Alessandro Braggio from Scuola Normale Superiore and NEST in Pisa, and also together with Alina Naricea from Buenos Aires, Argentina. This presentation is about a paper we have just published on Physical Review Letter last June, and the work is about the prediction of a local thermoelectric response in an hybrid topological Josephson junction in contact with a normal probe. And we used this non-local thermoelectricity as an evidence for testing the helicity of the edge states of a two-dimensional topological insulator. But let's go with the outline of contents of this presentation. First of all, I will show you the general idea and a bunch of motivations that driven us toward this work. Then I'll give you some details about the system we are considering. As you understood, it is an STIS hybrid topological Josephson junction in contact with a metallic probe. Then I will describe the physical mechanism which induces this non-local thermoelectricity inside the probe by applying an external thermal biases between the two superconductors. Then I'll quantify this, this response in the linear response regime by showing you this Onsager coefficient. Then I'll present some useful experimental facts and I'll draw some final conclusions. But let's go with main idea. First of all, it is known that the clearest signatures of a quantum spinel phase at topological insulators is represented by the existence of this Kramer's helical edge states, which propagate in opposite direction with opposite spin. However, this very important property, which is the helicity of these edge states, is something very subtle and hard to be tested experimentally. Indeed, this is usually probed by using, very complicated whole bar geometries with 4 or more terminals. It's for this reason that we demonstrate instead that a simple non-local thermoelectric current can represent a unique tool for probing the helicity of these edge states in a very simple geometry. More specifically, we consider just one helical edge state of a topological insulator embedded inside a superconducting topological Josephson junction with the usage of an external magnetic flux, which in turn induces what is called the Doppler shift effect. Let me say also that our thermoelectric effect is something in nature very different from the conventional thermoelectric effects obtained in standard NS junction, in which they usually explicitly break particle symmetry of the systems, for example, exploiting Zeeman fields or, polarized probe. But in our case, instead, our effect relies on a completely different mechanism, which is based on the helicity of the edge states of the topological insulator under the action of this external magnetic flux. But let's have a look to the system. As I told you, this consists of just one helical edge states of a topological insulator embedded between two S-wave superconductors at 2 different temperatures. The left one is the hotter one at the temperatures T plus delta T divided by 2, and the right one is the colder at the temperature T minus delta T divided by 2, where delta T is indeed the thermal bias among them. The temperature of the probe is just in between and is equal to T. Also, this is not a necessary condition. Indeed, we have demonstrated that the thermoelectric current one can measure at the probe by putting a thermal bias delta T between the two superconductors does not depend on the temperature of the probe and also does not depend on the position of the probe along the helical edge states of the topological insulator. Let me say also that here the two superconductors are electrically grounded, while at the probe we have the application of this electrical potential Vn. There is also the possibility to apply a Josephson phase difference among the two superconductors, but the really important ingredient here is represented by the application of an external magnetic flux, big phi, which induces the Doppler shift effect. But in order to understand what is the Doppler shift effect, let us consider the Hamiltonian, which describes the system. The system indeed is described by this Bogoliubov-de Gennes Hamiltonian, which is particle symmetric by construction, which eigenspectrum is represented here. More specifically, here is represented the eigenspectrum of the homogeneous proximized topological insulators region. And in green, I depicted the right-moving quasi-particles, and in orange, the left-moving quasi-particles. You can understand the direction of the movers by looking simply at the slopes of these curves. Furthermore, dashed lines represents quasi-holes, while solid lines represent quasi-electrons. But let's come back to the Bogoliubov-de Gennes Hamiltonian. This contains in the off-diagonal terms the gap or the parameter, delta x, with rigid boundary conditions at interfaces, while in the diagonals we have this Hamiltonian, h of x and its time reversal partner, which instead describe the helical edge states of the topological insulator, with in addition the presence of this epsilon ds, which is the Doppler shift energy, which is directly proportional to the external magnetic flux phi. The role of this Doppler shift is that to shift, indeed, as you can see, the curves of the eigenspectrum, and more precisely, the strength of this shifting is given exactly by this epsilon ds. You know, when this Doppler shift energy equals then the gap, then this parabola touches the zero energy level. But now, in order to grasp the physical mechanism which induces the occurrence of a thermoelectric current in the probe when one applies a thermal bias between the two superconductors, let us consider the case in which we are in the linear response regime, where Vn and delta T are very small, and also for simplicity, let's consider the case in which this difference, delta minus epsilon ds, is of the same order of the thermal energy of the system. That means that in this case, we are just exciting the states available at the bottom of this parabola, which are constituted mainly by right quasi-holes, right-moving quasi-holes, and left-moving quasi-electrons. Because they move in opposite directions, they thermalize with opposite superconducting reservoirs at different temperatures, and from this imbalance of cold left-moving electrons and hot right-moving holes, that inside the probe we get a net thermoelectric effect when Vn equals 0 and delta T is different from 0. We can have also the dual, Peltier cooling effect by considering Vn different from 0 and delta T equals to 0. This is the main physics under this non-local thermoelectric effect, but let's now quantify it. In order to quantify this effect, we exploit the scattering matrix formalism by computing the charge and its currents at the different terminals of our structure. And more precisely, we consider the case of a linear response regime by computing these Onsager coefficients. Because here we are dealing with two thermodynamical affinities or forces, the N and delta T, we end up with a 2x2 Onsager matrix, in which in the first line we have the linearized charge current at the probe, Jn, and in the second line we have the linearized heat current at the left or equivalently at the right superconductors. Here, L11 and L22 are local Onsager coefficients, while L12 and L21 are non-local Onsager coefficients. These are represented here in terms of a density plot as a function of the Doppler shift energy and this parameter, the square, which is just a parameter describing the coupling of the probe with the helical edge states of the topological insulator. Here, L11 and L22 are just, proportional to the charge and the thermal conductances. And let me say that these two quantities have been also studied in literatures, even if in the tunneling regime, when the square is very small, or without the application of any probe. So in this sense, we complete this analysis by considering any kind of coupling between the probe and the helical edge states. But the most important quantity here is represented by this non-local thermoelectrical L12 on-target coefficient, which, as you can see, is mainly different from zero just when the Doppler shift energy, epsilon ds, equals plus or minus delta. This corresponds to the situation in which one of the parabola touch the zero energy level, and this is the case in which we have a maximization of these fluxes of cold electrons or hot holes, or hot electrons and cold holes. It depends on the sign of the external magnetic flux. Let me say also that from the on-target coefficients, it is possible to obtain the so-called Seebeck coefficient, which is just a measure of the thermal voltage induced by the application of an external thermal bias, delta T. And as you can notice, this can reach very high values of the order of 60 or 70 microvolt per Kelvin, which is comparable to that obtained in ferromagnetic superconducting system, for example. Let me say also that a very similar non-local thermoelectric effect, but with a Seebeck coefficient 1 order of magnitude weaker, can be obtained in the very same setup, but without the presence of any external magnetic flux. This is what we have described in a very new paper we have just published on the archive, in which we obtain the same almost non-local thermoelectric effect, which can be just tuned by changing simply the external Josephson phase difference among two superconductors. Of course, this non-local thermoelectric response relies on a different physical mechanism, which is different from the one belonging to the Doppler shift effect, and is more because of Andreev interferometric effects occurring inside the junction. But again, here, this effect does not depend on the temperature of the probe, does not depend on the position of the probe along the edge states, and of course, does not require the application of an external magnetic flux. And for this reason, it can be a promising scheme for experimental validation. And for this reason, I also invite you to check this out on the archive at this link here. I have almost concluded, so let me just draw some briefly conclusions. First of all, we understood that it is possible to obtain nano-local thermoelectric effect inside an hybrid topological STAS junction without breaking particle symmetry. This effect is characterized by a non-local Seebeck coefficient, which can reach very high level values comparable to that obtained in ferromagnetic superconducting systems. This effect can be exploited as a probe for the important property of the helicity of the edge states of a topological insulator, and also on an experimental point of view, this effect does not depend on the temperature of the probe and its position along the edge, and also a similar effect can be obtained without the application of an external magnetic field. So with this, I have finished. So just I say thank you, and of course I'm waiting for questions if you have.
Okay, thank you, Gian Michele. Also, we have plenty of time again for questions. So, who wants to start? Any question?
Rafa, I have a question.
Yes, please, Alfredo.
What is so you in the case where you have the flux was the mechanism to break the symmetry, and which one is in the absence of the flux?
In the absence of the flux, the mechanism is something related to Andreev interferometric mechanism. That means that quasi-particles and quasi-holes coming from different superconducting reservoirs have a different dependence on the Josephson phase difference among the superconductors. And when they arrive into the probe, they do a kind of interference pattern, and that lets the emergence of this thermoelectric current inside the probe. So it's different from the Doppler shift, because Doppler shift is mainly based on this shifting of the parabolus or the spectrum of the system instead.
But sorry, then these two are linked. I mean, if you put the flux, you also put the phase difference in the junction.
We're talking here about Josephson phase difference. So you just apply this Josephson phase difference through a a non-dissipative current through the superconductors. Instead, in the other case, you have a magnetic field which induces a magnetic flux and then induces the Doppler shift effect instead.
Well, experimentally, it would be difficult to get this separated. But anyway, that's good. Thank you.
Okay. Any other question? Please raise your hand. Okay, I have one, so I can, while the other questions appear, I can do one. I can understand that the position of the probe plays no role in the thermoelectric response because you have the helical edges.
The temperature of the probe doesn't play any role. You can understand this by looking at the expression, for example, of the charge current inside the probe. This can be factorized, this integral in energy can be factorized in these three terms. And as you can see here appears just differences of Fermi function in the probe and between the two superconductors. This Fn plus is for electrons and Fn minus is for holes. When Vn is equal to 0, these two quantities are the same. So because these Fermi functions are the only one which have memory of the temperature of the probe, this, the dependence on the temperature of the charge current in the probe disappears completely. And this is important because this effect does not depend on spurious, gradient between the probe and each superconductors, but just depend on the non-local, let's say, thermal bias applied among the superconductors.
Yeah, but why it doesn't depend on the temperature of the probe?
Because as a combination, because of symmetry, yeah, you're right in a sense, because of symmetry of the system. So helicity, so yes, basically maybe because of the helicity of the topological age.
Because some channels compense the opposite ones. Right?
Kind of.
Okay, okay.
I would say more that is a particle symmetry. It's still particle symmetric.
Yes, it's particle symmetric plus helicity.
Yeah. Okay, thank you. So, if I see no more questions, I thank you again for the talk and for sticking to time. So we are surprisingly doing very well in this respect. So then next one is Alessandro Romito from Lancaster, and he will talk about the heat pumping in Majorana systems, operations on Majorana systems. So,
okay. Hi. I think.
Yeah, everything is fine.
Can you see everything?
Yes.
Okay, so let me start by joining all the other speakers in thanking the organizers for putting together this program in these unusual conditions. In my talk, I would like to discuss heat transport associated with quantum systems that show topological properties. This has been already the subject of many other talks today. The focus of my talk will be on the dynamics of the system, topologically protected dynamics, namely the braiding of Majorana 0 modes. The results I'm going to present have been recently published, appeared in a couple of papers, and they are due mostly to a student of mine, Tom Simmons at Lancaster University, and collaborators from Ben Gurion University, Kenneth Maiden, and a student over. What I would like, the three main points I would like to cover in this talk are essentially to give an overview of the physics of the Majorana, which we already heard about, so would probably can be very quick on that. But I would like to focus on the dynamics of this system, namely on the exchange and braiding of these topological excitations. And then we would like to discuss heat pumping associated with this kind of cyclical processes, and to identify in which way this heat pump reflects the topological nature of the system. And if I have time, I hope to tell something about the thermodynamical property of this processes by looking at fluctuation theorems associated with this transport. So the starting point is a system, a model that we have seen all across all the talks today and in the previous session. So it's the simplest of all. We have two leads, which can be a different voltage bias and held at different temperatures. And in the middle, there's something that makes energy transfer or electric transfer across the leads. And the specific of this talk is that we're looking at the system which has the topological properties. And specifically, we're looking at a one-dimensional two-wave superconductor. The peculiarity of these systems is that it has Majorana zero modes. So let me spend a couple of minutes to say what's the physics behind these states. This can be captured in a very, very simple model. Probably most of us know it. I will review very, very quickly. So you can think of this system in a very simple model, which is a toy model, which is just a lattice model, in which you have some kinetic energy for spinless electron and some pairing. The peculiarity, the superconducting pairing, the peculiarity here is that the pairing is a P wave, so between nearest neighbors in the simplest fashion. What happens in this system, it can be easily seen by looking at each fermion in terms of its Majorana component. So each fermionic degree of freedom is seen as two independent degrees of freedom, which are these Majorana modes. Now, what this Hamiltonian does is that it's able to give you the modes of the system. The excitation of the system will consist, this happens at least in this simple fashion in some limits, consists of coupling of Majorana on different sites. So all these Majorana are recombined together into fermionic degree of freedom, which are gapped, and you're left with some ungapped degree of freedom, Majorana degree of freedom at the two ends of the wire. So your Hamiltonian has gapped state, and you're left with a fermionic degree of freedom, which is delocalized and consists of some weight at the edge, at the first edge and the last edge of the wire, and this costs you no energy. So this appears in a many-body picture as the Janet ground state. If you look at it in the Bogoliubov-de fashion of particle formalism, this appears as a gap around the Fermi function, which is delta, and then you will have two levels at zero energy, but these two levels will be physically separated and be located at the end of the wire. So the physics we are interested in is the physics due to this particle. And the peculiarities are that these energy levels are stuck at zero energy, protected by topology and symmetry. And this is a single fermionic level, which is essentially non-local. The consequences of that, and the reason why this system was originally so interesting, is because you can manipulate them. And essentially, if you're able to exchange a position of these two particles in real space or in parameter space, which the process called exchange, and you can do it in an adiabatic way. Here I depict a way to do it in a network. So you can take one Majorana, move it that way, take the other one, move it across, and then finally move the previous Majorana at the end. As a result, you have exchanged these two Majorana, and this results in unitary evolution of the state in the ground state. And this unitary evolution is completely fixed only by the statistics. Here in this formula appears just in phase of pi over 2. The fact that this number is completely fixed is a consequence of a topological protection, and actually is the direct consequences of topological protection for this system. We have seen this picture already several times today, but let me review it again. So this physics I described can be engineered in nanostructures, and actually that's been happening since the last almost a decade now. what I reported here, the idea, the simplest idea that that was originally implemented is to use a semiconducting wire with spin orbit coupling and use standard superconductor in proximity and magnetic field to conjure up the physics of 1D spinless P-wave superconductors. And here is an experimental an apparatus doing that. Is the first one realized in Delft in 2012. And in these systems, one can measure transport, and actually transport is the original key that's been used to identify signatures of this Majorana physics. So essentially you connect this to an external lead, can be superconductor, normal. In the setup we are considering, we have this 1D P-wave superconductor coupled to normal lead. The presence of this Majorana gives a resonant and rev reflection essentially, and this results in characteristic transport signature. I reported here the data from the first original experiment, and the key would be this peak at zero energy, which ideally should be quantized. In this experiment was not, because many other effects take place, and like temperature can smear the peak. But ideally you would have conductance, zero bias conductance, which is quantized in units of 2e squared over h. This as far as electric transport is concerned. But this electric transport, of course, can capture signatures of the Majorana physics, but also has some limitations, I would say. So the Majorana are essentially neutral particles, which gives some symmetries between certain processes of electrical transport and prevent, for example, the transmission of charge across an infinitely long or extensively long wire. And also these limitations don't exist for neutral currents. So there's been a number of work that try to look at thermal properties and thermal transport in these systems. Many have been reported in today's talk. Here I just flashed several others. The focus on my talk is to make a step forward. So all the properties been discussed in the, concerning the heat transport in the paper I just flashed has to do with the static properties of the system, namely the fact that there are protected zero energy modes, and the fact that these states can be delocalized. As I said before, there's more to that, and this is braiding. So the fact that you can manipulate this system, and this manipulation manifests is the probably direct manifestation of the topological properties of the system. Now I have to say that while for all the previous properties they are accessible, even if are not easy experiment, they are experimentally accessible. I'm not aware of any experiment at the moment that can realize a braiding. Nonetheless, that's the key feature of this topological system. And theoretically, and when experimental will become available, I think it's relevant to establish what are the transport property associated with this key topological property of the system. So that's what we are trying to do in this talk. So the idea is to consider a system which hosts Majorana, realize a protocol, a cyclical manipulation of the system that perform a braiding of this Majorana, and analyze the transport properties and see whether the transport property can show any signature or reflect any signature of this topological protection. So the system I would like to discuss, would like to use as a model to analyze this property is a simple system which has been already proposed before as a possible way to realize braiding of Majoranas. Let me go through it rather quickly. So this white junction that you see here is our system in which we plan to manipulate to do the braiding. What we'll do, we'll add some leads. We couple two of the Majorana to external leads that we kept at different temperature and different chemical potential in principle. So the Hamiltonian is rather simple. There are, of course, the coupling between the system and the leads. which is standard coupling, and leads are just free fermionic, are treated as free fermionic systems. Now, due to the Majorana existing at the edge of the system, the coupling, the standard coupling between the fermions in the lead and the Majorana is constrained to take this specific form. And gamma X and gamma Y are the two Majorana which are coupled to the leads. And HY is the Hamiltonian of the Y junction. Here is where all the manipulation happens. Now, all this manipulation concerns the low energy physics of the system, so can effectively be described only in terms of the Majorana existing at the end of the wire. So as you see, this system has 4 Majorana. I can briefly describe what happens here. Let me do this way. So the system consists of 4 Majorana, and you have 3 of them at the end, and these 3 Majorana can be coupled to the central one. In this language, couple means that you take the Majorana close enough, or in some way you let them interact such that they become no more zero energy states, but they get split. So out of these 4 Majorana, which in principle give you a 4-fold degenerate ground state, when you pair 2 of them, they will be gapped, and the other 2 will remain as a degenerate ground state. So the idea of the manipulation is to pair this Majorana with the central one in turns, as you can see from the sketch of the plot here. So this manipulation can be absolutely generic as long as they are done slow enough compared to the gap of the system. And the other criterion is that at any time, there should be one coupling which is maintained to be 0. Under this condition, the system has, at any moment of time, has a 2-dimensional degenerate ground state, which means always at 0 energy level. And what changes is the coupling of this 0 energy level to the different Majoranas, to the different leads. This, as I said, this is the only property, which means that the results that I'm going to present will not depend, we will see at the end, on the specific shapes, neither from the maximum nor the specific shape of these curves that one is using. And this is one of the consequences of this topological protection. So the analysis is based on scattering theory, which works perfectly well for this system, since it can be described by single particle physics. So we define heat current as the weighted with a difference between ingoing and outgoing current of electrons, where the outgoing is obtained from the ingoing one from scattering matrices. Now, the peculiarity here is that this is a driven system, so the scattering matrix changes in time in a periodic way. We can then use a Floquet theory to describe the process. And moreover, we are interested in the adiabatic limit, so this allows us to expand scattering matrix around its adiabatic evolution. I will not go into much details of the technicalities, but essentially all the physics for the adiabatic limit can be captured by an instantaneous scattering matrix, which consists of an elastic contribution and the first correction to that due to the adiabatic driving. And this includes essentially scattering via the nearest bands, which happens to be at frequency omega, and at the end the frequency is sent to 0. The total charge pumped around charge or heat pumped around the cycle is obtained as an integral over time of the instantaneous currents. Here, just to notice, you can obtain exactly in the same way the electric current, just replace the energy everywhere with the charge. Now, this is an old formalism, and it's everything well known. What is usually done is you replace this scattering matrix at a given energy with, you neglect the energy dependence, and you replace it with the energy dependence at Fermi energy. That's good enough to give the leading contribution to transport. If you do that, you obtain an electric current which is proportional to the driving, and you obtain a heat current which is next order in the driving, order omega square. This means that when you will go and look at the total charge pumped over a cycle, you'll obtain a fixed term from the electric current, while you will obtain a vanishing term of the heat current when you send the frequency to be very small. Now, what does it change to this physics when you have Majoranas? As I said, the presence of Majorana just constrains a lot kind of coupling that you have with leads. as a consequence of that, this essentially particle symmetry, you obtain that this contribution is identically zero. This means that in our system, we need to release this kind of assumption that we can assume that the scattering matrix is just that at Fermi energy. We need to take into account the energy dependence of the scattering matrix. This doesn't change this result. This, as I said, depends on symmetry, and this is preserved. So we don't pump any electric current. Of course, when I talk about pumping here, I assume that both leads are kept at same temperature and same temperature and zero voltage bias. But because we release this approximation, we obtain a heat current which comes at order omega, and therefore we can obtain a geometric contribution when integrating over a period, geometric contribution to the pumped heat across the system, and that's what we calculated. Well, as per the details of the calculation, one can go through all the scattering metrics and calculate them analytically for this very simple model. And let me tell you what are the results. So as I showed, there is no charge pumped by the driving. As I said, this is a consequence of particle symmetries of these Majorana zero modes, but there is a heat pumped in this kind of systems. And of course, this depends on the temperature. Again, it's not temperature bias, it's overall temperature of the reservoir. And the interesting results, and that this heat pumps essentially depends on nothing but the temperature. So if you take the limit in which the temperature goes to zero, you obtain a universal value, which can be related to some geometric property, which is fraction of the sphere spanned by the parameter space. But that's a side comment. The important thing is that these results does not depend on any of the parameter. Doesn't depend on the, I mean, being an adiabatic process, we know it doesn't depend on the speed at which we run the parameter driving, but it also does not depend on the height of this curve delta that I showed you before, or the specific shape that we are using. Another character, this is a direct consequences of the topological protection of this system. It will be insensitive in particular to local fluctuation in time of your driving protocol. Another characteristic is that the heat exchange at one end and at the other are anticorrelated, and this is consequences of the fact that these are Majorana end states, which has correlation between the Majorana at one end and at the other of the system. So the heat exchange at one lead is correlated with the heat exchange at the other lead, actually anti-correlated exactly in this limit. I think I have a few more minutes, so maybe I can tell you a bit more about that. So once we realize that you have essentially you can drive a system in a cycle and transfer heat from one reservoir to the other, we thought about asking a bit more about the properties of the thermodynamic properties beyond the average current of this process. Now, a standard way to do this kind of analysis is to look at the total statistics of the heat transfer. Well, that's, I think it's pretty hard to measure experimentally, so this is a purely theoretical aspects, I would say. But there's something interesting about that, and this has to do with fluctuation theorems. So one aspect for this kind of system to fulfill fluctuation theorems, and this is take the form of, they have many forms, but one can be used very efficiently for this system is that of Galavotti-Cohen fluctuation theorems, which is expressed here in terms of the probability of transfer a certain amount heat cube between one leads and the other in a certain amount time tau in a long time limit, and corresponding process in which you transfer the opposite amount of heat. You can formulate that in terms of full counting statistics of this heat transfer. And this theorem would amount to the fact that this particular quantity, this figure of merit, should be zero. Now, it is known that when you have geometric contribution to this heat process, this has nothing to do with Majorana physics. It's more generic, it works for a simple quantum dot. You will get correction to these fluctuation theorems, and these corrections are geometric in nature. Since we are doing an adiabatic process, we obtain exactly the same result. So you can see here that this probability distribution is asymmetric. we are holding the temperature to be the same. So we expected 0 here. So the asymmetry of these curves shows that this theorem cannot be 0. So there's some correction term. And here you plot explicitly this correction term in terms of the counting field statistics. But again, as I said, this is a general result of geometric terms due to adiabatic driving. What is peculiar about this term is that this correction term also reflects some topological properties of our system. Specifically, this correction term, do not depend on a specific, on the specific of the driving cycle that you're using. So different driving cycles, as long as you're in the adiabatic limit and you realize one of these exchange of the Majoranas, you will obtain exactly the same correction term. The other peculiarity is that in this system, due to the maintaining the degeneracy at any time, we are able to realize this correction to the fluctuation theorem just by controlling the parameters of the system, namely the phase of the coupling to the external leads, while for other non-topological system, one always has to perform cycles of external parameters, like in the space of temperatures of the corresponding leads. I think that I conclude with that, and I will just summarize my main messages. So what I did, I hope I showed what's the basics of Majorana physics and the braiding. I showed that when you perform this kind of dynamic operation of the system, you're able to pump it between the two leads. And this heat has some properties which are universal. And in this sense, they reflect the fact that this is the result of a topologically protected operation. Thank you.
Okay, thank you, Alessandro, for the talk. We are a bit out of time now, but not too much. So if there is a fast question or a couple of fast questions, we can still do it. Okay, I see some connection of your heat pump in this system with the adiabatic pump for charge. For example, this work by Brouwer some time ago.
Yeah.
Do you expect the same kind of deviation for the fluctuation theorems expressed for charge in that case than what you see for heat here, or?
Well, no, I think, I mean, the fluctuation theorem are typically thermodynamics thermodynamic properties, so they do not, I mean, they apply to heat, charge, transfer of energy, not transfer of charge. You cannot write a theorem of that sort.
Well, yeah, you can do if you have, instead of a temperature difference, you have a voltage or something. So you can do it, for example, for work instead of heat.
Well, but these are yeah, but they are associated with I mean, this theorem follow essentially from the entropy, from the positivity of entropy production, and you don't have something like that for charge. So I don't think that you can obtain a theorem of that sort if you do it for charge. At least I'm not aware of any.
Yeah, well, you can express it for work.
Oh yeah, you can. Well, no, I mean, you can. So you expect okay? You want to expect you're thinking of having the energy due to the fact that you have voltage bias in that case.
Yeah, yeah. If you apply an opposite voltage bias and you drive current against it, something like that.
Well, I mean, that would be some sort of out of equilibrium situation, because I mean, when you have a temperature in the reservoir, then you can treat them as equilibrium system, right? While if you have voltage bias, then all your process will be some sort of out of equilibrium transfer from the thermodynamic point of view. So anyhow, I'm not aware of. I mean, one can try to do the same kind of calculation for voltage biases. But I'm not aware of any fluctuation theorem that has voltage biases instead of temperatures here. my suspect is that with voltage biases, again, you're looking at some sort of out of equilibrium processes, and I'm not sure that you can do that. But the honest answer is that I don't know.
No, okay, good. Okay, so if there are no further questions, thank you, Alessandro, again.
Thanks.
And then we change from one Alessandro to the other and come back.
So I should stop sharing.
So next one is Alessandro Braggio, and he will talk about non-equilibrium Josephson junctions and effects related to that.
Do you see me? Do you hear me?
Everything is fine.
Okay, thank you very much. Okay, I also want to thank the organizer to give us the opportunity to live this experience of online conference. And since I have the last person of the session, and probably I have also the duty not to be too achieving. And the title is not seems scaring, because when you speak about non-equilibriums, people and Josephson junctions start to be complex. But anyway, I will try to convince you that even using really very simple tool, you can get a very strange effects, and also some of them can be very useful. In particular, we will consider the problem of a Josephson junction, as you see in the figure, where you can get two different, you have a gradient of temperature in the Josephson junction, and you also consider the possibility that the two materials have different gap. And these simple things that seems not so complex, even to be done experimentally, honestly, it seems to generate a huge amount of new physics, in my opinion. And this means that we need to look better this type of system, in my opinion. And I want to thank firstly the young people that work on those two. Essentially, I speak about two different group of works. The first one is Giampiero Marchegiani that shared with us the thermoelectric adventure in Josephson junction, and Claudio Groccello that is now in Salerno, and he will speak. I will discuss about the current jump phenomenology in Josephson junction. All this research will done certainly with a collaboration and continuous exchange with Francesco Giazzotto, that was a fundamental asset to many ideas and so on. Okay, let's change the. Okay, many of you have spoken about thermoelectricity, so. Essentially, I can do quite fast here. Essentially, I take also the argument of the quantum transport, so Landauer approach and so on. And many of you have claimed that, okay, in order to get thermoelectricity with the gradient of temperature, you need to add an asymmetry in the transmission matrix, or in the transmission that the transmission, the energy dependence of the transmission should be hot with energy. So essentially, this tells you that thermoelectricity and superconductivity is maybe not so nice things to mix, because superconductors are natural are naturally particle symmetric. By the way, so essentially, but if for this talk, for the moment, we concentrate only in the tunneling limit. So in a certain sense, the complexity is even reduced. And we consider just a tunneling element that is even energy independent, as you see here. I take it energy independent. And the only energy dependencies come from the density state. Okay, in that case, you should say, okay, look, in that case, if you don't touch spin degree of freedom and so on, I mean, with the superconductor, you should not have any thermoelectricity. And I want to show you that this is not true. Okay, and essentially, this is indeed why I make this sort of comma with this without touching spin symmetry, is because it has been demonstrated in the ferromagnetic superconductor, where you combine superconductor with the ferromagnetic insulator, or anyway, if you have an exchange field, you do the spin splitting, was discussed before. You can create a very strong figure of merit for thermoelectricity, and it was even measured actually. So in a certain sense, okay, superconductivity is not true that is not helpful for thermoelectricity. Even the nice things of the superconductor is that a peak density state that is very helpful for thermoelectricity if you are able to provide it. And we studied it also those systems, and we make proposals of high sensitivity thermometry and so on. But what is important now, I want to concentrate that here you look the IV curves, and you see immediately that they are particle break. And essentially minus V and plus V are asymmetric. And you see this is in certain sense a signature that you have a thermoelectricity. That is, you are in this position here or here. Essentially, so the idea is that, okay, but still, okay, if you want to keep the particle symmetry, still you can have thermoelectricity. Okay, this answer was essentially, if you ask me maybe 2 years ago, I would say no, you will not have thermoelectricity. But in the last few years, there are some works that explore this possibility, that making some clever advancement or using non-locality, as was discussed even in an experiment today. I was also involved in this research, in this type of research, or by even using the SNS system, paper by Glatzman and others, or even in the topological insulator, as we see for the talk by Gian-Michele. Using non-locality or other features, you can, in certain sense, generate thermoelectricity. So, but here I don't want to use those tricks. I want to stick to a sort of tunneling approach. And so you need to go beyond, necessary to go beyond the linearity, because if you take the linear regime, by definition, the particle symmetric system, you cannot have a thermoelectricity. And so you use this expression for the current and for the heat transfer in a junction. And I taken the superconductor model, the most simple model that you can imagine. And also you can assume that, okay, maybe this can be normal metal or can maybe different materials such as superconductors, just changing the density state. This is essentially the fundamental tunneling approach to the junction. And with this simple expression, this simple formula, it's interesting because you can demonstrate that it is energy conserving, so respect the first law, and also respect the second law. Okay, so it's serious. I mean, it's not a stupid formula. And you can demonstrate using gate essentially by consequence of second law that if you are in equilibrium, there is no way your system should be dissipative. So this means that the system is resistive. Okay, in any case. But if you can go out of the equilibrium, such as, for example, different temperature, this could happen that the system becomes thermoelectric. Thermoelectrics, what does it mean? It means that you provide a bias, but the current goes against you because the system becomes active and it produces current against the bias. This is something that is a battery, essentially. And obviously, you can see this as a sort of absolute negative conductance effect. And now, this is probably the most important slide of the talk. Okay, I just provide you the receipt. Okay, how to generate nonlinear thermoelectricity in a very simple way, in a universal way also. Let's assume that you start from the same temperature, 0 temperature, and we consider this type of expression that I showed you before, and we assume that we consider, okay, certainly always particle symmetric density state is a metal, is a constant. Let's assume that we consider a metal with the constant density state. In that case, you can easily realize that the current, it should be always, really always dissipative, because even at finite temperature, essentially you have no way to have thermoelectricity, because even if you put a gradient of temperature, you cannot have any thermoelectricity in this system. Now, I propose you this trick. Let's assume that you put a gap on the hot side. And now it's clear that you have to consider the contribution of the particle and the contribution of the hole. And now you make use of the particle symmetry or the symmetry with the energy of the density state. And you can change this form of the whole contribution, and you can get a final formula that takes this shape. And that's, looking at it, you realize something very weird. That, okay, if you're a gap density state, you have a temperature that is comparable with the gap, so it can provide quasi-particles over the gap. You can essentially see that the current sign depends on the sign of this term. So this means that you can, if you are able to change the sign of this, you are able to have thermoelectricity in a very simple way. And this can be done assuming that you have a monotonic and decreasing density state. If you do that, even in the finite, in the small bias limit, you get thermoelectricity. And indeed, if you put this type of shape to the density state of the other lead, you get thermoelectricity. Or eventually, as this is completely general, so even a molecule will work in this way. But if you provide another superconductor as a Josephson junction, you have also thermoelectricity. So you get a thermoelectricity in a system that at the beginning is purely particle symmetric. In a certain sense, you are telling that the system starts to be purely particle symmetric. Due to the bias, you become non-anymore particle symmetric in the transport and the system, so you generate the thermoelectricity. This is essentially the mechanism. Okay, there are some rules in the mechanism. Essentially, you need to have the gap on the hot side is bigger than the gap on the small side. And so this means that you should consider gaps that are different in size, not so much difference, because we consider, for example, a difference of 30%, even 70%, so not so much. Okay, you can provide also experimentally, essentially. And here you see exactly what happened to the IV. You see that with the same IV, with the same temperature, you have the green line, a standard SIS junction. With a gradient of temperature, you can get the matching peak, and it's still dissipative because in this size, IV is positive. But now, if you put the gradient temperature, as I told you before, you get thermoelectricity. And not only, but this thermoelectricity is very interesting because it's a linear in bias. So even at small bias, you get thermoelectricity. And this tells you that this is a spontaneous breaking of the particle in the Josephson junction that provide you thermoelectricity. So it's something spontaneous, not external, it's intrinsic. Okay? And obviously, you can increase the bias and you can get nonlinear thermoelectricity and so on. Okay, now the question is, I present your IV and I promise you, I want to show you something, IV that is completely odd you see that there is a completely odd symmetry between this branch. And this is exactly the fact that the transport, the IV is completely, in a certain sense, particle symmetric. And this is something that you can do only with this game, with the superconductor, actually. And but you see that depending on the temperature that you put the hot side, let's say, you can get thermoelectricity. It is the Chan line. And you see that is the analytics that I showed you before, the formula that I showed before, wonderful fits the results that you get numerically, making the numerical interpretation of the formula. And with this analytics, you can calculate even which is the slope of your linear thermoelectricity. And you predict that, so you have absolute negative conductance. And this is really a signature of thermoelectricity. But I discovered another thing that I was shocked when I discovered it, that you have two different Seebeck voltage. And this is the most clear character of the fact that this is starting from a system that was a priori not particle, it was a priori particle symmetric. Because when you have a system that is particle symmetric, there is no more P or more N character. It's just, it chooses by itself, by breaking the particle symmetry, in this case, and you can get the P character or the N character, and you have exactly opposite symmetric Seebeck voltage with the same gradient. So you not need to change the gradient. You just keep the same gradient, and you can get two different solutions, one positive and the other negative. This is really a strong signature of the fact that you have a spontaneous breaking of the particle symmetry. And you have also, you can evaluate the power in the linear bias and so on. And now the question for me was, come on, but SIS was studied 50 years and we take really the most simple integral that we can do and we make it and we discover something new. Is possible that the people not consider it? And actually we look at very carefully in the to show, okay, this is a standard results where it was discussing the effects of thermoelectricity in superconductor, but there is no sign of this discussion that I'm giving. This paper in the 60s, okay, always there is a paper in the 60s of some Russian guy that did this. And in a certain sense, they did it. But unfortunately, they did it in a way, assuming that you have a photoelectric effect. So you have a shining light and you excite it, you have a non-equilibrium electron distribution in one side of the junction. They realize essentially the physics because they realize that you need to have a different gap and so on. But you do not realize that you can do in much easier way with the temperature gradient. And there is this paper that I was really scared because the figure is also the same that I showed you before. But they consider the effect that due to the fact that you have the tunneling matrix element that is energy dependent. And this effect is 10% much smaller than ours. It's a 10% respect to the fact that I reported now. So, and so they say, but okay, but these are purely theoretical guys. And the funny thing is that there wasn't even measured, because it was a mismeasurement where they put negative, where they put non-equilibrium distribution, the Josephson junction, and they see exactly the AV curves that I showed you before. So when we saw this picture, I say, come on, they even measure it. But the problem, they did not know that because it was using this non-equilibrium distribution effect. So this is certainly something that in PISA we wish to measure is in a controlled way with a temperature gradient to see if you have this non-equilibrium effect. But now, so I used to say to you that the effect is purely nonlinear. This is due to the spontaneous particle or symmetry breaking in the system. Okay, and it's very strong. I mean, it's 350 microvolt on Kelvin. It's huge. It's huge because it's very peaked at the necessary state essentially. And also the thermodynamic efficiency is quite high, 40%. It's a non-equilibrium. This is absolute efficiency. Yeah? It's not typically the ratio between efficiency and Carnot efficiency that becomes when the gradient of temperature become very small. So in a certain sense, this is absolute efficiency. I mean, this is a good thermoelectric machine. Okay, maybe I want to show you, and probably I go to conclusion that the question would be, okay, what you can do with that? Okay, spontaneous breaking, you can do a thermoelectric memory, because essentially the system may have two points, okay, that you drive the system in this point and stay there, or you drive the system in this point and stay there. So with this point is given by the bias at the junction. So this is really non-volatile thermoelectric memory. But also you can get an oscillator because depends on the resistance of the load, you can even a stationary oscillator. Now the question for you will be, now, is the Josephson effect destroying the thermoelectricity? Has essentially the same Gisburg quoted in this long time ago, in this original paper. And essentially we discovered this, we studied this effect with the critical current. And it's funny because also the critical current has an intriguing effect when you have a gradient of temperature. And you see in this picture, where essentially increasing the temperature on one side, the hot side, you see they have increasing of the critical current. That's something that for us was very astonishing, because typically with the temperature you reduce critical current. And we use also to write the sort of calorimeter according to the presentation of the first speaker today. And this calorimeter is very good, there's very high dynamic range, very good resolving power, and this work in the dissipationless regime. But so I need to answer to your last question. Is the Josephson effect destroying the effect? No. We make the sort of an analysis where we can tune the Josephson effect, okay, using this type of system where you are doing a sort of interferometric technique to increase and reduce the weight of the Josephson effect. And we was able to show that even with the moderate reduction of thermoelectricity, of Josephson current amplitude, you can get thermoelectric effect. And the funny thing is that this thermoelectric effect is also, I mean, is also reflected in the Josephson frequency, because as the opposite is the Josephson junction, so the Josephson frequency is fixed by the bias. So you get thermoelectricity at DC voltage, and over it you have a fluctuation of the bias that is exactly given by Josephson frequency. So I think that I need to conclude. Okay, thank you very much. If you are interested, you can look the references.
Okay, thank you, Alessandro, for the nice talk. You also answered your question, so I don't know if the audience will have more, but now it's time to do them. So please raise your hand if you have any. There is no in the chat. Well, what determines, maybe you said and I missed it, what determines the position of the peak?
The position of the peak is the matching peak, when the two gaps match. Okay, and this is the two gaps are different, so you need to have a slighter bias. Okay? But the funny thing is that I think that the best question that I leave to you to think about is a spontaneous break in symmetry, and where is the interaction?
But why do you call it spontaneous? Because this is due
It's
to the
spontaneous.
voltage, no?
It's really spontaneous because I mean you don't do nothing essentially.
Apply a voltage.
You put the junction, you put a gradient, and you wait, and spontaneously sometimes it goes in one Seebeck effect, in one Seebeck sign, or sometimes in the opposite Seebeck sign. And this is just selected by the fluctuation. It's really spontaneous. And the real point is that because of superconductivity, even if you have in the tunneling limit, is an interacting system. You live in interaction. Yeah. And you are seeing a spontaneous breaking induced by the intrinsic interaction that there is in the superconductor. This is exactly the point.
Okay. So we have a question from Jonas Rico. Okay. So the question is, could you say a few words more on the anomalous Green's function and how it emerges in the context of Josephson junction?
More words in the sense that, I mean, you can calculate I think that you are thinking about the critical current, because the anomalous Green function comes in the critical current part of the story, okay? And in that case, you use a standard tunneling approach, okay? And you get this formula that I reported here, okay? Where you see that you take into account that you have different temperature. Probably, or eventually you are telling me, you are asking me, I mean, are you completely solved the problem with non-equilibrium? No, obviously. We are assuming that the time evolution of your system is low in comparison to the intrinsic time scale that is given by the gap. But this can be tuned. We can find parameter where this approximation is sufficiently valid. So in a certain sense, we are doing a adiabatic analysis. Actually, all this time-dependent behavior is done in sort of a adiabatic analysis. But it's valid also in non-equilibrium, taking account this quote.
Okay, so if there are no more questions, I would like to thank Alessandro and all the speakers of the session, and also all the participants and everybody who submitted the abstracts to the mini-colloquium. I think it resulted in a very broad interest colloquium with many different subjects that we treated and many different aspects of thermoelectricity. So thank you all for participating, especially in this special occasion of the online conference, which is new to all of us. I think it went quite well. So I would also would like to thank Isabel, who was helping us a lot with the organization of the meeting, even if she was silent most of the time. So thank you very much, Isabel.
Thank you, thank you.
And now we have the last picture for the session. So if you want to switch on your cameras, we can take it. We are not so many today, so. Who's taking the picture?
I'm doing.
Ah, okay.
So it's mine. Okay, done.
Very good. Okay, so thank you again, and see
you very much
in a real conference at some point. Okay, so that's it.
Yeah. So
it was very nice, no?
Yeah. Yeah, we survived. No major. Yeah, a nice mini colloquium with a lot of participants.
Yeah.
I would say more than average.
Listen, yeah. Today there was a little bit less than other days, but yeah, other days it was around 40, 50. Today also 40, something like that. So yeah, it was very nice.
What was the average in the other sessions?
What?
Sorry?
What was the average in the other sessions?
Well, it depends on the mini-colloquia, but around 30 something, so 40. But the first 2 days, there was almost 50 participants in your mini-colloquium. So.
No. Very successful.
Yes.
No, I think it was quite nice. Well, you always miss the chatting with people and commenting and things like that, no? And coffee breaks and this. But okay, considering the situation.
Yeah.
It was funny that in the first session, everybody wanted to ask questions only by the chat.